Okay. Meeting is now streaming live on YouTube.
We cannot hear you, Yomila.
Sorry. Let me just wait until that connects through. Okay.
Meeting is now streaming live on YouTube.
We're on YouTube, and I'm just going to make you host.
We cannot hear you, Yomila.
Sorry. Let me just wait
happening?
until that connects through.
No.
Yeah, that was the YouTube. It's 10 seconds delayed.
Okay.
Sorry. Okay, so you guys are good to go.
Okay, so now I'm host, and the streaming is going on.
Perfect. I'm gonna press record as well. I'll just leave it all recording, and then we'll trim everything.
Okay, cool.
All right. Please ask host to give you permission to record. Okay. Can I please have host back?
How do I do it?
Here, no? Record.
No.
Record on this computer.
No, because I have to give permission to Jomila.
Are you able to record?
I am able to record.
Okay. Then you can hit record whenever you guys start.
Okay. So when the official starts.
Sorry, I mean.
And it'll ask you.
Sorry, I've never done this before, so.
That's okay. It'll ask you if you want it on the cloud or on your local computer. Just pick the cloud.
Okay.
Okay. Thank you so much, guys. We'll see you soon.
See you, and
Good luck, Yomila.
good luck.
Nicola, is your hair only from lockdown, or was it already long before COVID?
No, yeah, it's long since 2015.
I can't hear anything.
Can you hear me?
Oh.
Can you hear me, Elio?
Yeah, I can hear.
Okay. No, it's since 2015.
Okay.
So, how about yours?
This is only from lockdown.
Okay, good. No, and the beard is super recent, like 2 months old.
I had a beard until 4 days ago or so.
So you shaved for the workshop, or?
No, I shaved because I don't know. I can't handle having a beard that's longer than a certain length, and then I'll start just constantly playing with it.
But because that is the limit for a person can suffer the beard, but after that you get used to it and it becomes okay. So you just have to pass that week, and then
okay.
It's okay.
I'll try again sometime.
So how are you doing?
Okay, it's our final, and I was getting an exam yesterday.
So I couldn't hear you for something like 15 seconds. Sorry.
I was saying it's our finals week right now, and I was giving an exam yesterday. So it's very busy, and I'm short on sleep, and now I have to do a lot of grading. But it'll all be over in about a week, and then I'll be able to do research again.
Cool.
Yeah.
And how was the vaccine going? Did you got a shot?
Yeah, my wife and I got vaccinated. But Mississippi in general is kind of far behind the US curve. They have a lot of local political pressures from people who are
fans of freedom and
right.
We are on YouTube.
Yeah. Okay, true. I'm not saying anything wrong, hopefully.
No.
And which courses are you teaching? For which you have exams?
One of them was pretty good. Electromagnetism for undergrads, for physics majors. That's fun. I try to teach them tensors early. I'm not sure if they appreciate it or if they enjoy it. But I try, every time there's a cross product or something, I try to also do the problem using tensor notation and La Vita, and I don't know, they probably don't like it, but anyway. And then there's a general physics for non-majors class. That's the one with a lot of grading. There's pre-dental students and pre-medical students and so on.
Okay, so for like non-physics faculties.
Yeah, and they don't know calculus, so I had to. It's been a very long time since I've done any physics that did not involve calculus, so I had to remind myself how to do that. We don't have Lagrangians in this course, right?
I don't know, this reminds me of high school where we did covered most of all physics without calculus, and I still don't understand how we managed.
Right. Yeah, I mean, I think a lot of these students might not have had any physics in their high school.
Okay.
Anyway, how are things going over there?
That's good. So it's slowly reopening. Like now they reopen the restaurants since Monday.
You're in the office? Yes,
we are actually in the same office.
I figured that out.
Did you?
No. In the office we can stay without the mask.
Yeah, but with 1 meter.
Okay. No, it's just he's one of the few people I interact with every day, so we decided to live without mask.
Did you get access to vaccines?
Yeah. We got the AstraZeneca in end of February, was it? The second shot in 10 days, 2 weeks. So yeah, but also Italy in general is pretty slow. I would say European countries were behind, but I don't know. It's kind of reasonable.
Yeah, I don't know. It's all kind of surprising. The infrastructure is all there, right? As compared to in the US where there isn't a universal health care. So how
But it's probably mostly because of the doses. We didn't get as many doses as other countries in the world, which made more pressure, probably. So I don't know. Also, I remember Miguel was shocked by the infrastructure of Italy when people were taking our names in a piece of paper, so without computers and anything. I know. Probably it's because they did it in 2 days. They didn't have time to organize stuff well. I don't know. So I have to make the speakers co-host, right?
Yeah.
So Tony.
Hi, Tony.
Hi. Hi.
Hello.
Nice to meet you.
Teaching. I've just arrived. Hi.
We are.
Shall I send
Say
an
again?
email to Jaumila? Shall I say Jaumila that I'm here so that she gives me?
No, you
co-host,
are
privileges or
co-host now.
something?
You are co-host now.
Okay. Thank you.
Yeah, because I'm being the host, because Jamila cannot do it today.
Yeah.
So I get permissions.
Helvi.
Hi, Helvi.
Hi,
Hello.
Helvi.
Hey, Miguel.
How are you?
Good.
How's
How
it
are you?
going? Fine, fine. Thanks. Thanks for joining as well.
Do we
So-
still have a moment to test slides?
Say test.
You can do it now.
Yeah, you can do it now. Yeah.
Okay. Okay. Very good. Let me just see. Okay. So I will share the entire desktop because then. Okay, so you can see my presentation, right?
Yeah. Perfect.
Okay. And the other thing, let me just try. You can also see the animation.
Yeah. Perfect.
Fantastic. Thank you.
Hola, Pau. You are mute.
Hola, ¿qué tal? ¿Cómo estás? Decía.
¿Tú?
Mira, por ahí, sobreviviendo.
Sí, estamos todos igual. Vamos, que se puede. ¿Quieres probar la slide? Tony, tú
Sí.
también. Si
A
quieres.
ver, un momento.
Va Pau primero. Después.
A ver. Ajá. Un momento. Vale. A ver.
Again,
Eh?
who's the discussion session leader?
Eugene.
Eugene. Okay.
Vale.
She's not here yet.
Sí, se ve. Perfecto.
¿Todo bien?
Todo bien. Animación también. Dale.
Venga.
Perfecto. Perfecto. Tony.
Yeah.
¿Quieres ver tu slide?
¿Podemos probar? Sí. Genial. ¿Compartir pantalla?
Sí.
Hey, Miguel.
Hi, Enrico.
What's up?
Here. I am the chair. We are testing the slide.
Good, good.
This group is
Do you
very
see
good.
Do you see it?
Yeah.
Okay, great. Thank you.
Perfect. Thanks. Okay, so 2 minutes.
Yeah,
Then
let's wait.
say again.
Let's wait a few minutes because usually
Yeah. Yeah.
people increases.
Yeah.
Yeah.
Should I also put
Hola, Isabel.
Enrico as host?
If you want.
Yeah.
Idea.
Enrico, I will make you a co-host as well.
Thanks. I
Just
shouldn't
in case.
do any work.
Jaumila. Hi, Eugene.
Hello, everyone. Hi.
Hey, Eugene.
How are you?
Hi, Eugene.
Wow, and 6 days of conference.
Yeah.
You guys are
Yeah.
really attempts. I must say that this is not easy to sit on a Zoom meeting.
No.
It's so much more exhausting than anything else.
We wanted to hold it in person, and we thought by April surely we'll have improved.
Yeah, and we don't even get a nice big conference dinner as reward, right, for us being diligent.
Right.
This week seems to be particularly popular, right? Because there are 2 other meetings happening at the same time.
Yeah, who scheduled everything this week?
I don't know.
There was another one besides the APS meeting.
Competitive conferencing, this one. Oh, anyway. Oh gosh. Oh, we're in the middle of trying to buy a house. We were selling our house, so it's all very, very complicated in the last couple of weeks.
Goodness. Have you found one, Eugene?
No, we haven't found one. We have sold ours, so we have no place to stay. Like,
Goodness, then you're technically homeless.
I will. Yeah, basically, technically, we'll be like technically homeless, carrying our baby. Like moving from street to streets.
You're homeless with a baby. Goodness, that sounds awful.
Anyway.
Thank you. Oh. Hey,
My baby.
So we're gonna wait a couple of minutes and we will start.
Yeah, I mean, I haven't. To be honest, I haven't been going to all the talks, but I've been to quite a bunch of them, and I think it's been a really, really good conference. It was really nice, and hopefully, one of the things I've noticed about the panel discussions is that it seems like Zoom conferences, people seem to be more ready to participate because the panel members are not sitting on the stage, and people feel a little bit more open to just speak up.
Yeah. Let's see how it's going today. The best day.
Last day. It's Friday. Right?
Yeah.
Wow.
Okay, Enrico, shall we start?
Yeah, I guess we can start.
Yeah.
Luis is yeah, sure.
Continue.
Hi, Luis. You're welcome, of course.
So, okay, we are going to start. So, good morning, good afternoon, good night to everyone here. Thank you all for being here, participating here. This is the last day, the best one in this workshop. So, just a few words on behalf of the organization. We would like to thank to all of the speakers, moderator discussions for their talks and willingness to participate in this event. So we are going to start with Leo. So Leo, do you want to share your screen? And just a few words. Remember that we have the Slack. Seba, can you put the link, please? And remember as well to switch off the microphone and raise the hand. So thanks, Leo. So Leo is currently an assistant professor at the University of Mississippi. Leo has a vast experience in strong gravity and numerical relativity, and today he will talk about an approach to taming secular instabilities in numerical simulation of beyond the Earth theories. Thanks, Leo, again. Go ahead.
Okay, thanks, Miguel, and thanks to Enrico and Jamila and everybody who helped organize this nice workshop. It's early here, and I haven't practiced this, so I'll try to stay on time. But let me know if I'm running slowly. So please yell at me if I need to speed up. And maybe I need to skip some things, and I have some material that we could move to like the discussion session. All right, so probably I don't need to convince anybody that we need to test general relativity. We know that it makes sense as a classical theory. It doesn't make sense as a quantum theory because we, at some energy scale, run into new physics, and just naive quantization doesn't work, and you need an infinite number of counterterms, and so on and so forth. So, a lot of people are interested in testing general relativity from different approaches. Some people's approach is to, use fancy high energy theory and try to completely rebuild the theory from scratch. I instead take a more pedestrian approach, which is that we should ask nature what's going on. So we should do low energy model building. We should do precision tests in every regime where we can test the theory. And until 5 years ago, we only had access to theories in the weak field, unless you think cosmology is a strong field. And a lot of theories are the same as general relativity in the weak field. But now that we have gravitational waves, we have access to strong curvature and nonlinearities and dynamics in general relativity. So the goal is to be able to test general relativity in that regime. And we want to do precision tests, which for my purposes means we want to use binary black hole mergers. Don't have to worry about the unknowns of nuclear equations of state. And of course, we just have many more signals from binary black holes than from neutron stars. And so the question is, how do we perform precision tests of general relativity with binary black holes? Well, there are different approaches. If we're being purely phenomenological and not worrying about model building, then we can just parameterize at the level of the observables, something like the parameterized post-Einstein formalism for gravitational waves. So generally, you could just take your predictions from general relativity and you could just multiply them by some other factors that change them in some way. So power law correction to the phase, change fractional correction to the amplitude that also runs like a power law in frequency. And then you try to look for these coefficients and bound them. And of course, LIGO has done this. And LIGO and Virgo collaboration have released these constraints. This is just the first constraint, and they've improved a little bit. But if we're interested in learning something about the strong field, then we should think about whether or not this ansatz really makes sense here, where the post-Newtonian formalism breaks down. So it doesn't really make sense to expand things in power of the frequency, which is powers of V over C of the binary. So instead, parameterizing is great, but it would be nice if we had guidance from specific theories to know if our parameterization really makes sense. So we would like some, ground truth from actual theories predictions, because otherwise, if we see some discrepancy between the observations and the predictions, then we don't know whether or not those discrepancies are because there's something wrong with our modeling or because something is wrong with the data. So you need ground truth, and you need to know like the level of the systematics in your modeling. Okay, so we want to be able to specifically simulate binary black hole mergers in theories that are not GR. And so Helvi will talk about this as well, and Pau will talk about this as well. And so let me go very briefly through some of these things. So of course, the Einstein equations are extremely beautiful, but if you want to put them on a computer, or if you analyze the structure of partial differential equations, they become much less beautiful. So you have to formulate it as an initial boundary value problem. And people have been doing this for many decades now. So of course, the structure of the equations is that they're nonlinear partial differential equations, second order. They're quasi-linear, which is important for what I'll be talking about later. People have been trying to do black hole or just numerical relativity in some form since the 1960s. I guess this should now say 16 years. I didn't update this slide, but now we can finally merge black holes. And so I get to shamelessly show this movie from the SXS collaboration because it's very beautiful. So this is just visualization of some spatial slice through the simulation, through the orbital plane. Okay, so we have these fully nonlinear simulations for general relativity, and we understand how it works for GR. So now, okay, to do this in GR, it took a long time, starting in the 1960s, and there were a lot of difficulties. And a bunch of the difficulties came from the fact that the theory is under-constrained and over-constrained. There's gauge freedom, so that's the sense that it's in which it's under-constrained. There's also constraint equations, so it's over-constrained. So you can think about there being some infinite dimensional function space, and the solutions to general relativity live on some constraint submanifold, which is typically an unstable submanifold. So if you make numerical errors, you blow up off of this. But people have since then figured out how to do constraint damping and good gauge fixations and avoid the generic singularities which are inside of black holes by, say, cutting them out. Great. So that's sounds hard, and it was hard. And so every theory besides GR will be at least this difficult, because every other theory of gravity is as difficult as general relativity. Okay, so here's the plan. I'll tell you a little bit about analytical progress in understanding whether or not theories have a good initial and boundary value problems. Maybe I'll skip this stuff and we'll talk about it in the discussion session. I'll mention a few good theory, in a sense, good theories where there's there's a known good initial and boundary value problem. And then what I'll be talking about is what do we do with bad theories, where the only approach that we have, as you'll see, is perturbation theory. And there's a problem that perturbation theory runs into, which is that it'll have secularly growing instabilities. And so I've been working on figuring out how to control those secularly growing instabilities. They're not some sort of numerical instability. It's, well, we'll see exactly where they come from. And so I think that we figured this out in something called the numerical, what we're doing is numerical, but version of the dynamical renormalization group. I didn't make up the term, but anyway, we're kind of stuck with it. Okay, so let's tell you what we know right now. So there's a bunch of theories where there is a known good initial boundary value problem. Of course, there's general relativity. Scalar tensor theory, you can take scalar tensor theories and through some field redefinitions, just make it GR plus scalar fields. And so it has a good initial boundary value problem, but your black holes in these theories tend to shed any of their hair and become identical to black holes in GR. And so binary black hole mergers end up being the same as in general relativity, unless you have some mechanism for having them hold on to their hair. So for example, Einstein-Maxwell dilaton also has a good initial boundary value problem. That's a theory in which black holes do hold on to their hair. They don't shed it. And there's some Horndeski theories where there is also a good initial boundary value problem. I guess Pau is going to talk about this. And actually Gauss-Bonnet is also a type of Horndeski. Okay, so in general, what you do is you look at the partial differential equation and you apply the method of characteristics, and you want to be able to show that it is hyperbolic. And so all of the speeds in the problem have to be real. If you have complex characteristic speeds, then you can't evolve it. It doesn't make sense as an initial boundary value problem. So the PDEs that are under control are first and second order PDEs. Although there's also a bit of work on taking higher derivative systems and turning them into first order time, nth order and space systems. And so you can actually apply the same methods there. I'll skip, okay. So, well, actually, I'll show you why quasi-linearity is important by example rather than talking about it. Okay, so here's a case that is known where there is something known about the initial boundary value problem. It's got a pretty complicated action. You add in a whole bunch of terms where you take all possible combinations of coupling second derivatives of a scalar field to the metric and curvature tensors, but you keep only the ones where once you take the variation of the action, you end up with equations of motion that only have second derivatives. So this gives you the Horndeski class. And there's a nice approach to this, which I have to say I don't completely understand yet, but there's a general harmonic-like gauge where you have hyperbolicity results. And Kovac and Rial showed that you can actually have strong hyperbolicity when the coupling is weak. So there's some epsilon that controls how far away you are from GR. And when that number is small, then we know that we have strong hyperbolicity. And a special case of Horndeski theory is Einstein-Dilettante-Gauss-Bonnet that Helvi is going to be talking about. So there's a way of writing it like this. This is not the Horndeski form, but you can do some field redefinitions and make it the Horndeski form. But its formulation has been studied in a number of papers, and most recently, Will East and Justin Ripley actually did numerical simulations at weak coupling in this theory, but fully nonlinear. Okay, and then there's stuff known about theories where what we know is that it's probably bad. And so I'll be talking a little bit about this thing called dynamical Chern-Simons. So I introduce it now. So it's just GR plus something that I'll call an axion-like field. And this axion being parity odd, we couple it to the leading parity odd curvature term, which is the Pontryagin density star RR. And it has some equations of motion, which importantly have third derivatives of the metric here. So the principal part has shifted away from being the Einstein part to being the C tensor that has the largest number of derivatives of the metric. And so a few folks, Terence Delsat and David Hilditch and Helvi Witek, suggested in this paper that it probably does not have a good initial boundary value problem. And I think there's another reference that I forgot to add here. Okay, so why is quasi-linearity important? Okay, so if you look at like this frozen field analysis, you take all of your fields and you expand them in very small fluctuations around some background solution to see how perturbations might grow. For those fluctuations, you solve for the highest time derivative, or you introduce auxiliary variables and order reduce. And so let's say that the highest time derivative appears in a form like in some Horndeski theories, box phi quantity squared. So if you solve for the highest time derivative on phi, you have to take a square root, right? And the stuff that's inside the square root could become negative. So I think that this actually happened in some people's attempts to do numerical simulations in some Horndeski theories. And once the thing under the square root goes negative, then your real fields suddenly become complex and stuff stops making sense. So this kind of thing doesn't happen when you have a quasi-linear theory, because the highest time derivatives of your small fluctuations on your fields will always come in with no higher powers than first powers. That's not really the reason why quasi-linearity is important, and you'll see that later. Okay, just to mention another one, Hassan-Rosen bigravity. I think this is a nice theory. It's got two metrics, an F metric and a G metric, and they're coupled only through non-derivative terms. So if you look at each of the equations of motion individually, it looks like there's just an ordinary Einstein equation for this metric and this metric, but then they're coupled through non-derivative terms. So those are only lower order terms, but you can't really, you can't study each of the equations separately. You really have to try to make the entire system hyperbolic at the same time. Anyway, so people have been working on, BSSN-like formulations of Hassan-Rosen bigravity. I think it looks kind of promising. Okay, so those are theories where we have analytical understanding of whether or not they have or lack a good initial and boundary value problem. So numerical progress, I guess I'll skip through a lot of these things as well because Helvi and Pau will tell us more. Okay, so scalar tensor theory was the first one where people were doing binary mergers, black hole mergers, full three-dimensional simulations. And that's because it's really just GR plus a scalar field. And the thing is that, as expected in these simulations, the black holes shed their hair unless you do some funky stuff and have either time derivatives or spatial derivatives of the scalar fields that you impose. And most recently, or as recently as I edited this slide, there were some interesting results from from a theory where you add a mass term to the scalar field. That gives you kind of a smoking gun signature where you get this kind of inverse chirp. Anyway, so people can do simulations in this theory, and we have predictions. But just a handful of simulations, not like the thousands that we have for GR. Okay, Einstein-Maxwell dilaton. There have been a few simulations as well in this paper by Hirschman and collaborators in 2017. So because the black holes in Einstein-Maxwell dilaton carry extra charges, they can carry an electric charge and a dilaton charge, which are related to each other in this theory. So as the black holes go around each other, think about it like just an electrodynamics problem. You've got charges going around each other. There's a time derivative of the dipole moment, and you've got these two dilaton charges going around each other. So you've also got a time derivative of the dilaton dipole moment. And so that leads to more radiation that carries away energy faster than in GR. And that's the real interesting thing about an in-spiral is how much more quickly it evolves than in GR. So strangely in this paper, it seemed like despite having huge coupling strengths, the binary mergers looked, I guess, pretty similar to GR. But anyway, please read their paper for more details about this. Okay, so this is the most recent thing that I've heard about, except that I will now hear about Helvi's and Pau's stuff today. So Will East and Justin Ripley did fully nonlinear simulations in Einstein scalar Gauss-Bonnet using this idea from Kovac and Papalo and Rial, where it's kind of a harmonic-like gauge, but you have like multiple metrics. Two of them are auxiliary metrics that control the characteristic structure of some of the equations, and this makes it possible to simulate. So they actually did black hole mergers at weak coupling, but still the equations themselves are treated completely non-linearly. And so we've got in spirals, at least one set of simulations in this theory, and we got radiation in the scalar field, radiation in the metric. Okay, so the difficulty with treating each of these theories as like an exact set of differential equations that we need to simulate is you pick a theory, you have to study the PDEs and see whether or not it has a good initial boundary value problem. You have to figure out which formulations of the equations will actually work on the computer. You have to write new codes. There's a lot of work to do, and there's a lot of theories to examine. So it seems like there's just a never-ending task of theories to study, and every single one, you need special techniques, special tools, special simulations. So the question is there something we can do to avoid this? Is there an approach that will actually like address all theories at the same time? And the answer is yes, kind of. And so you can look at it either from the point of view of we're doing perturbation theory, or you can justify it by saying every theory that we know about is really an effective field theory. And they all make sense within some regime of validity as long as you're below some energy scale. So yeah, maybe they stop making sense in terms of being well posed when you go to too high energies. But as long as the momenta are, as the spatial derivatives are not too short, then it at least analytically makes sense if you ignore those high frequency modes. Think of it as an effective fields theory, and it does make sense, at least analytically. Okay, and so when it is treated as an effective field theory, we should think that we have some hierarchy of theories, and there's going to be some new length scale that we expect to be a high energy scale, a short distance scale, because otherwise we would have seen it in nature already. And so in order for the theory to be under control, we need to have this hierarchy of scales. And so there's naturally going to be a small parameter that we can use as an expansion parameter. So whatever that scale is, if we take the energy in the energy scale in the problem, or the derivative scale in the problem, and do that divided by our new length scale, then we'll get a small parameter, and we can expand everything in powers of that parameter. So the example that I'm going to use for part of this talk is dynamical Chern-Simons. So actually, let me just blaze through these results. So I already showed you the action before. We've got these third derivative terms, and we've got some parameter epsilon that I'm going to use to control how we do the simulations. So what happens in this theory is that the Pontryagin density, which comes from parity oddness, sources the sources the axion. So for example, spinning black holes have scalar hair. So as we increase the spin of the black hole, we source more and more of this axion scalar hair for the black hole. Here it's mostly dipolar at low spin, and then it gets some complicated multipole structure at higher spins. Okay. So you can imagine what would happen if you put two of these hairy black holes around each other is that there's a time derivative, not of the scalar dipole moment, although there can be on spin precession times, but more importantly of the scalar quadrupole moment. And so the time derivative of the scalar quadrupole leads to quadrupolar scalar radiation, and that should make it inspiral more quickly. So in the post-Newtonian regime of this, we treated a long time ago, back in 2011. So you can do these calculations by hand and figure out how much more quickly will a binary black hole inspiral when it has this extra axion hair on the black holes. Okay, and the reason that we can do this, both analytically and numerically, is by using perturbation theory. So we take everything in the theory and we expand it in powers of this epsilon parameter. So we have metric plus epsilon times the metric perturbation h, for example. So when we take the Einstein equations, which had third derivatives of the metric, those third derivative of the metrics were multiplied by epsilon already. So that stuff all gets suppressed and shoved over to the right-hand side of the equations. So the principal part, order by order, is controlled by the principal part of GR. And you know that this is the principal part for GR is just box of the metric perturbations plus lower order terms. And this is perfectly well posed. So on a background, that's a GR solution. And that GR solution could be, a post-Newtonian solution where we do things by hand analytically, or it could be a numerical solution where we have the fully nonlinear background metric G and the metric perturbations H, which satisfy a linear equation of motion. So the moral of this story is that background dynamics are well posed, so the perturbations are well posed. And so that allowed us to do these simulations. Here I'm only showing the scalar field, but this is a background metric that's fully nonlinear. It's generating scalar radiation. You saw that both of those black holes in the strong field regime had scalar clouds around them. And so the time derivative of the quadrupole moment here is leading to quadrupole radiation, but then you get this burst of dipole radiation. So the phenomenology is interesting, but anyway, let's just skip to some results. So we did perturbation theory on this first just for the scalar. And so we got scalar radiation. Okay, let me skip all of this stuff because I'm running low on time. Yeah, we can extract the quasi-normal modes, etc. Okay. Okay, yeah, sorry. I skipped too fast. So we did metric perturbations in 2018 and then 2019. This work was all led by Maria Okunkova. So we got metric perturbations from a head-on merger and then from an in-spiral, but just very close to merger. So we didn't have a lot of in-spiral in these simulations. We started extremely close to merger. Sorry, I'm just zooming in here to show you the difference between GR, which is the dashed line. So this is psi4, the 2-2 mode of psi4. So there's the GR solution in the dashed line. And then according to perturbation theory on that nonlinear background, we've got some, if you crank up this coupling parameter, there's some small difference between the GR solution and the beyond GR solution. Okay, just a proof of principle that we can do that. Okay. But the question you should be asking yourself is, why did we not have any in-spiral in these simulations? And the answer is, if you start the simulations earlier and earlier before merger, then what you find is that the amplitude at merger for the perturbations is growing with how much longer before merger you started. And that's not physical. This is a result of using linear perturbation theory. So I'll show you, this is a totally generic phenomenon that happens when you do perturbation theory. And the reason that this happens is that, the real physical solution, the difference between the background solution and the physical one, is that you should have an in-spiral happening at a different speed. There's a new time scale, which is like how long it takes for the two solutions, the background one and the physical one, to dephase, right? So there's a secularly growing phase difference between the two solutions. But when we do these simulations, we are forced to use a background that is in-spiraling at the rate that the GR solution in-spirals. So it's physically incorrect in that sense to be using that as a background. And of course, I mean, we knew this back in the day, even when we did the scalar simulations, we were saying, here is the secular time scale, the difference between the GR simulations that we're doing and the real physical simulations. They have this extra time scale, which we're able to predict, using these numerical simulations. And when this time scale gets short, which happens near merger, then our perturbation theory is going to break down in this secularly growing way. So that's the thing that we have to be able to control. Okay, so let me show you how to control it. And to control it, let's go all the way back to, like freshman physics or sophomore physics or something. So let's say that we took a nonlinear oscillator and the nonlinearity is controlled by some parameter epsilon. It doesn't have to be small, but you could use this epsilon to find analytical solutions for this. So order by order, you expand an epsilon. So x0 just satisfies a simple harmonic oscillator. It's just, cosine of omega t is the solution there. And then when you go to the first order in perturbation theory, x0 appears on the right-hand side. This nonlinearity got shoved over to the right-hand side, just like GR plus beyond GR corrections. And, if you think about this, x1 has a natural frequency according to this equation of omega naught. And we're driving it with a source term that has frequency content both at omega naught and, harmonics of it. But the important thing is that you're basically driving an oscillator on resonance. And when you do that, you get a secularly growing mode, right? So x1, the solution, has t times sine of omega naught t. So it grows with time, times oscillations. So that's the naive perturbation theory point of view. But the real story is that we don't just have a correction in the amplitude like naive perturbation theory allows you to have, but rather if you do this thing called Poincaré-Lensted perturbation theory, which is a little ad hoc, you say, I know in reality that the frequency of this oscillator shifts because of the nonlinearity. And so if you pose that you just take a times cosine of omega t and you split omega up into omega naught plus epsilon omega 1, and then you re-expanded that, because if you're doing naive perturbation theory, all you're going to be able to do is to find the coefficient of epsilon. When you re-expand this, you just take a derivative and this omega 1t pops outside. So you get secular growth out here. And so the new time scale, the difference between your background solution and the real physical solution happens over a secular time scale, which goes like 1 over epsilon times omega 1. Okay, so that's the origin of this. And we want to be able to do something like this, but for beyond GR theories. So first of all, this thing right here is a little bit ad hoc. I mean, it works great, but you have to like know the structure of the problem and be able to like guess the right thing to do. That what we do is we correct the frequency. Okay, so now this dynamical renormalization group approach, DRG, you know, this was kind of brought to my attention by Chad Galley, but I think it came from high energy theory people. So Ira Rothstein is a high energy physicist. So this paper was totally analytical, and it did things just in the way that high energy theorists would do. So you started with your solution to they study the Newtonian two-body problem plus leading radiation reaction. So you get an in-spiral. And so that solution has, and you treat the radiation reaction as a perturbation. So the background solution has some separation, some frequency, some amplitude for, let's say, eccentricity, some orbital phase, and you promote them all to depend on some scale, which is like an RG scale. And when you do perturbation theory, you get secularly growing terms. So like a high energy theorist, you add counter terms to absorb them. You just look at the form of the perturbations that are there and you add counter terms. And you introduce some unphysical time, and then you scale set, and this allows you to extract beta functions for these parameters. And once you have those differential equations given by the beta functions, you can solve them. And then you plug that back into your original solution to basically resum the solution. So this is a kind of long, complicated procedure, and it works for something analytical. But what if you don't have an analytical solution? So this is what I'm interested in, because we don't have analytical solutions to the binary merger problem in GR, let alone when we go beyond GR. Okay, so this is probably the most important slide. I know that I timed this all wrong, but I think that if you should pay attention to anything in this talk, it's this slide. So here's the idea behind our kind of simplified approach to DRG. So let's say that what you're trying to do is find these scalar, these fields. They don't have to be scalars. Fields phi a. So if you did naive perturbation theory, you do phi a plus epsilon phi 1 a. And this whole thing is only going to work if, this could be in an infinite dimensional function space, but there has to be a lower dimensional kind of attractor manifold or slow manifold. So we have a finite dimensional parameter space. So for example, in the binary black hole problem in GR, you have an infinite dimensional space for the metric, but we don't worry about throwing all sorts of incoming gravitational waves into a binary black hole. When we're talking about quasi-circular binary black holes, it's only a 7-dimensional parameter space, right? So there's an attractor manifold there. And so the idea is that the secular growth in phi 1a is going to be absorbed by promoting these parameters to be parameters that flow under some beta function equation. Okay, so let's say that if we were to solve this equation for short times, then we would have our background parameters plus epsilon times, here's the flow at short times, so t minus t naught is short, times a, let's say, constant at this point, beta function. And alpha I introduce here as a kind of diffeomorphism. You'll see that later. But Chad and Ira already had this. And this is, this alpha is like shifts in parameters that are time independent, and beta is time dependent flow. So when you plug this into your background solution, phi 0, and you re-expand, the same thing happens as in the harmonic oscillator, the nonlinear oscillator, right? So we plug it in here, and then when we re-expand, we end up taking derivatives of this background solution with respect to this finite number of parameters. So there's a function space for linear fluctuations, and it is spanned by functions with this known ansatz. So we need...
Leo, can I ask you a question before you see, because yes. I'm getting a little bit lost here. So is lambda parameterized the possible manifold? Is lambda sort of like manifold, like lambda is not a dynamical variable, right? It's parameterized all the possible manifolds that you can solve on the background. Is that what it is?
Yeah, in the GR problem, that's exactly right. Each
Okay.
lambda point is a whole spacetime.
Okay, good.
But a 7-dimensional space of
many
spacetimes.
parameters. Yeah. Okay.
Yeah.
Thanks.
Thank you. Okay.
Sorry, Leo, 5 minutes left. But...
Thank you. Yeah, so terribly timed. I'm sorry about that. Okay. Good. So when you re-expand, this epsilon shift in lambda is what's multiplying these differentials, right? So phi 1, this secularly growing solution, should look like these growing functions. And you'll see that they are growing, right? Because if you start with a slightly different spacetime, then you get a slightly different, as time goes on, the in spiral and the two spacetimes happen at slightly different rates. Okay, so that's what this is. So when you match between your secularly growing solution and your space of functions that should span it, which are also secularly growing, then you can extract the beta functions at a particular point lambda of the background. So that's the whole point. The secular growth encodes the beta functions for the renormalization growth. So the secular growth is something that you need to be able to find if we're doing naive perturbation theory. Yeah, it looks like it's bad because it's growing in time and it's unphysical, but you need to be able to solve for it so that you can extract the beta functions. Okay, so just to, yeah, I'm sorry that I'm going so slowly, but so here's the geometrical picture of what's going on. We have a finite dimensional parameter space lambda, and it'll have some flow in it, and then we'll have our solution manifold S, which we'll have a flow of solutions. Every point in this manifold is an entire solution for the function. And so when you flow, you go from one solution to a different solution, one spacetime to a different spacetime. And so in the parameter manifold, we can have just a time-independent diffeomorphism. That's what alpha is. So that's just a diffeo, but also a time-dependent diffeo, beta. And so actually, our background solution could already have a beta function, a beta 0. And we need that for GR because we're going to think of our betas or our parameters as being something, like separation is one of the parameters. But then we correct the beta function at order epsilon and at higher orders. So what we need to do is we need to undo the background flow, do a diffeomorphism so that we can reparameterize if necessary, and then do the corrected time-dependent flow. So we undo the beta 0 and then we apply the beta in the end. And so instead of that naive thing that I wrote down, this thing is just kind of to give you an idea of what it looks like, but you can expand this using the Baker-Campbell-Hausdorff formula. Oh, sorry, I wanted to give you this other picture. So look at a tangent space, right? So we have a map from a fully nonlinear solution to a fully nonlinear solution. But when we have we have a map from parameter to fully nonlinear solution. But when we have this map, we also have the differential of the map d phi. And that gives us a map from small changes in the parameter, so a vector in that tangent space, to linear fluctuations around this nonlinear solution. And those linear fluctuations have a component that's in the tangent space of the solution manifold spanned by those differentials, the delta phi d lambdas that we need to expand in. Okay, so like I said, using Baker-Campbell-Hausdorff, you expand this, you can go up to whatever order in time and epsilon you want. And so this is the parameter vector v that lives in this tangent space over here. And then you do the push forward and you get a vector in the linear vector space of linearized solutions around that background solution, which multiplies those differentials, delta phi, delta lambda. And using that, you can then extract from the solution alpha 1, beta 1, and whatever constant coefficients come up in here, right? The alpha and beta at a point are just constants. And so you can do that at a given simulation, lambda 0, and then you do it, and then you repeat over parameter space at a bunch of different lambda zeros. And so just as a proof of principle, we did this using the KdV equation. So the KdV equation is nonlinear, just like the Einstein field equations. It has, solutions that kind of like hold onto their own structure, solitons. That's like a black hole. And then we deformed the KdV equation by adding this epsilon delta x squared term. And this term is like a drag term. So when you add this, first of all, we can solve this fully nonlinearly just to check, but we can also solve it order by order in epsilon. But when you do it fully nonlinearly, this drag term means that your solitons, instead of going at a constant velocity, they slowly lose velocity, and so their amplitude also changes. But that's exactly, that's supposed to be mimicking what happens when you add a correction to GR, that the kind of secular displacement of the system, so the position as a function of time, is going to get a secular difference from the background. So think about it as in the background, the soliton would just translate linearly with time, but when you add epsilon, then it decelerates. And so you'll get a growing difference between the background and the correct nonlinear solution. Okay, so here's what this looks like. Let me pause this for a second and show you what are the curves that are on here. So the fully nonlinear solution is the black dashed one. So that's the truth in a sense. The naive perturbation theory is the pink one. And so it is forced to kind of track the location of where the background soliton is, and it will blow up with time. You can see that already at time 5.5 here. It started to get, like 50% as big as the background solution. And the blue is the dynamical renormalization group flow that we've applied by extracting beta functions and so on. And so if I let this run, you see that the naive perturbation theory has just totally blown up, and it's tracking where the background solution is. So the background soliton is over here, but the nonlinear soliton, or the one that is decelerated, is over here. So it's lagging behind. That's the secular difference between them. But our dynamical renormalization group flow is tracking with the fully nonlinear solution. Okay, so let me close this and just tell you, how do we do this? Well, so here's our background solution. Of course, this one we know analytically. And it has a background beta flow. It has that its position translates with V, so its background beta function is V d by dxc. And so, okay, the nice thing is that we know the background solution, so that means that we can just take these derivatives to figure out what functions will span that linear vector space of growing solutions, that, secularly growing solutions. So we just expand our solutions that are linearly growing in time, or linear and quadratically growing in time, in terms of these functions. Of course, we don't have that luxury in GR, but we can discuss how to do that with a numerical background instead of an analytic background. So here's what it looks like. So each of these wiggly things is a snapshot at a different time.
Sorry, Leo, 1 minute.
Okay, thanks. So the red curve is the numerical solution, and the blue dots is what we get when we fit to, this function that we know of time, this function that we know of time, times some stuff that comes from taking those Lie brackets that I showed you coming from Baker-Campbell-Hausdorff. And so those Lie brackets, that they give you exactly what you would expect from, like, freshman physics, that an alpha function in velocity is a velocity shift, and a beta function in velocity is an acceleration. So you get 1/2 acceleration times t squared. And so the fits perfectly recover what we get from the numerical perturbation theory solution. Okay, so this is kind of a space-time diagram showing that once you match, then you're left with this residual, which is log of, log of the residual is some very small negative numbers or very negative numbers. So the residual is tiny and it captures beyond secular effects, but let's skip that. Okay, so this is the alpha of V. We do that at a bunch of different soliton speeds. So that's a bunch of different points in parameter space, and we can construct these fits to the beta function. Here I blew up the errors by a factor of 10 to the 7, just so you could see them. And so the beta function looks like it's just a pure power law in velocity. And so that's how we're able to then flow the background parameters. And so here's our reconstructed background flow, a space-time diagram again, where colors are the values of the function. And so the renormalized solution now flows just like the background solution does. And so this is the difference between the renormalized solution and the fully nonlinear background solution. And there's some phase error still. So here by time 50, there's a phase error of half of the width of the soliton. But you can just look by eye and see where would the background soliton be by this point. It would be all the way over here instead of over here. So this is like, our goal is to be able to get this to 1 radian in the inspiral problem. All right, so sorry that I went over time, but the idea now is to apply this dynamical renormalization group approach to beyond GR simulations. And so from each beyond GR simulation, we can extract a value of the beta function at a point in parameter space, and then we need to do it over all parameter space so that we can interpolate through the parameter space to get a beta function, to get a full beta function flow that we can integrate to kind of resum the beyond GR simulations. And we can apply this to any beyond GR theory that's close to GR. Okay, and then we go back to studying waveforms and predicting things for LIGO and finally testing GR. Okay, so what do I want you to remember? There's this approach to doing beyond GR simulations for theories that are close to GR using perturbation theory. So you don't have to do it on a theory by theory basis. You just expand around GR. You will get secular perturbations, but remember the moral is those secular perturbations encode the beta functions, which you need to then tabulate and interpolate and then use them to flow the solutions so that we can resum the beyond GR solutions. Okay, so there's a lot of work to do still, but hopefully it works. Okay, so sorry I went over time, but I'd be happy to take questions.
So thank you so much, Leo. So we have time for a very short question and then move on to Helvi, and then we can discuss in discussion session. Please save all of the questions, please. So go ahead, Eugene.
Hi, Leo. So thanks for the talk. It's very interesting. So I mean, I guess in the KDV questions, in a sense, you kind of have the background solution, right? So what have you tried, instead of going straight into beyond GR theory, have you tried to think about, say, collisions of KDV soliton? That seems like in my view, the more logical next step. Like,
so we didn't try this, but if you go back to this article by, I'll get the reference. It's around 1999 or so. There's this paper on the dynamical renormalization group, not numerical, right? Because as far as I know, it hasn't been done yet. Where they treated the interaction of two solitons using the dynamical renormalization group. So yeah, I think that's possible. We didn't try that yet, though. It's a good idea.
So Luis, please.
Hi. Okay, thank you. Hi, Leo. Luis. Thanks. This is a nice talk. I mean, I as you know, we have a different way of thinking about this, but any method that's trying to chip away on all these questions is worthwhile. So I am actually pretty interested in the way you're going after now. But I just have a very simple question. any method that we, at the end of the day, we latch onto as being perhaps the way forward, should at least do some of these simple problems right. So suppose I have this following equation: box of phi equals some lambda, that's the scale of box of phi, box phi square, or gradient of phi square to box of phi. So if you try your perturbative way, you'll get nothing, right? Because the order 0 is box of phi equals 0, and I have thrown in the right-hand side precisely something is always proportional to box of phi. So my perturbations will always be staying me in the box of phi equals 0 problem. So would you say this renormalization will go around that? And how?
I think that's a very good example, because I think that's very similar to what happens when you put your background field in a vacuum state, and when you're applying the effective field theory approach, when you integrate out that field, you have to integrate it out in its background, in its vacuum state. So yeah, it's true that if you integrated the field back in and went to very high energies, that you could get that that field out of its vacuum state and have large field excursions and things like that. But when you integrate it out and it's in its vacuum state, then you restrict yourself to some submanifold of solution space. So there is some space that's kind of out of this manifold, and field and fluctuations of like the field, exciting the field out of its vacuum state are the solutions that you're talking about that cannot be recovered from this approach. So that's a very good point. You are restricted to this idea that you're like at a sufficiently low energy scale that you're not going to be exciting that field out of its vacuum state. But I think that people would tell you that, these are the correct solutions, the one where you stay near this manifold if you're doing it at sufficiently low energies.
Well, so maybe just before, maybe we can take this offline, but if we think of a box phi equal lambda box of phi, that we can solve the full problem. And indeed, this is something in a very short time scale, you get arbitrarily close to the solution of box of phi, just that. However, there are slight offsets in now your solution. And from there on, sure, you're latching on to a box phi equals 0 solution, but your solution is slightly different from the one you would have obtained had you followed from box phi all the way through. So now you have introduced a small drift. So when I think of LIGO or telling LIGO anything, I'm worried, oh, we could be telling LIGO, look left, when in reality, the solution is right.
Yeah, I mean, so I think that the alpha and beta functions should capture that small drift.
All right, we cool. Yeah, maybe we can take this offline. I'm interested in understanding how you would go about that. Thank you.
Okay, thank you, Liv. Thank you, Leo, again. Very nice talk. So let's move. So Helvi, if you want
also, I'll stop sharing my screen then.
Yeah. Right. So, Helvi, are you there? Okay, so the second talk is given by Helvi Witek. Helvi is an assistant professor at the University of Illinois Urbana-Champaign. Her works cover a large range of topics in astrophysics, cosmology, and numerical relativity. Today, she will talk about the adventure of black hole, the case of quadratic gravity. So go ahead, Helvi.
Okay, thank you, Miguel. And good morning or good afternoon, everyone. It's a great pleasure to be here today, and I would like to thank the organizers, Jamila, Enrico, Miguel, Nicola, Sebastian, Marco, and Mario for organizing this really wonderful meeting. And today I will talk about the phenomenology of black holes and black hole binaries in quadratic gravity. I will focus on one class of theories, which is scalar Gauss-Bonnet gravity. And I will also take this opportunity to really highlight some recent work that we have done together with Hector Carrera Silva, who is a postdoc at AEI, one of my PhD students, Matt Ali, and one of my colleagues here at UAUC, Nico Yunus. And the other paper that I would like to advertise was really led by Banafshi Shiralilu, who was a PhD student in Amsterdam, in collaboration with Tanya Hindra, Samaya Nasanka, and Mr. Ortiz. Okay, so as you may guess from the title, I shamelessly borrowed that from one of my favorite books, a collection of books, which are Arthur Conan Doyle's Mysteries of Sherlock Holmes. And the reason why I like it so much is that it summarizes the scientific method as little else, and at its time was really revolutionary. And one of my favorite quotes, if I may cite it, is the following. So here Sherlock Holmes said that it is an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. So in some sense, we are trying to play detectives for gravity, try and understand the mysteries of nature. And in order to do that, in order to exclude the impossible, we really have to understand all pieces of the puzzle, all kinds of predictions that we can have within general relativity as well as beyond GR. So in this analogy, the mysteries of nature I would collect in like 3 main topics, where observations tell us about an additional component of energy labeled as dark energy that becomes relevant on very large scales. We know from observations that about 80% of all matter is non-baryonic. We don't actually know what it is, and so we label it dark matter. And I believe you have seen a very nice talk by Katie Clough at the end of last week, where we try and use black holes interacting with ultralight fields to understand about dark matter. By the way, I'm not going to talk about this here, but we are also finishing up a paper with my other PhD student, Giuseppe Figueras. So if you want to learn about that, please invite him for a seminar. And the last question is, what is quantum gravity? That seems like almost the holy grail in physics. And at the moment, we have a bunch of candidate series of what quantum gravity could be. General relativity itself is not a good candidate for that. So we typically have to go beyond Einstein's theory of gravity and have to extend it. In all of these, we can now perform new tests of both general relativity and extensions thereof in the strong gravity regime, because we have observations of black holes and neutron stars and their gravitational wave emission. So in some sense, we will now use black holes and gravitational waves as our gravity detectives for new physics. And as I just said, we actually have the data to do so. So here I'm just showing you the collection of events that LIGO, Virgo, and Kaga collaboration have presented. So here we have the mass of the compact objects detected. We have neutron stars observed with electromagnetic observatories here in yellow. The neutron star mergers detected by LIGO and Virgo here in orange. Black hole candidates detected from X-ray observations here in purple. And then the collection of about 50 gravitational wave events from black hole binaries here in blue. That is to say, we do have data now, and there's much more to come in the future. So we do have the data to test gravity, but what about our theories? Do we have theories? Yes, as I've seen in Leo Stein's talk just now, there are plenty. And one of the questions that I think we will discuss later on is which ones are actually the most interesting ones, or the best motivated ones. And also, as you have seen, we are really on the way to provide observable predictions. So at the moment, we are still lacking, for example, complete inspiral merger ring-down waveforms to perform strong field tests of gravity beyond parameterized tests. So we really, are going on this program and trying to provide predictions for gravitational wave signals and extensions of GR. I will focus here on one class of theories, and in particular, I will focus on the scalar Gauss-Bonnet gravity. I will write down the action in a moment, but think of it as essentially a theory that is like curvature squared. Yeah, so one of the main motivations to look at this is that it will give us insight about higher curvature corrections that become relevant when curvatures are high. So you might find that becoming relevant near black holes. And these theories are also inspired by the low energy limit of certain types of string theories, inspired by compactifying Lovelock's gravity, which in more than 4 dimensions, which gives you the most general theory of gravity in 4 and more dimensions that have second order field equations for the metric. Okay, so let's become a bit more precise. So the action of a scalar Gauss-Bonnet gravity is written down here. You have your Einstein-Hilbert term. You have a coupling to a scalar field here. This is just the standard kinetic term. And then you have this coupling here in the middle, where alpha GB is a dimensionful coupling constant. F of phi is a coupling function that I will talk about in a bit more detail in a moment. And then this curly G here is the Gauss-Bonnet invariant. So this particular combination of Riemann squared, Ricci tensor squared, and Ricci scalar squared that still gives you at most second derivatives of the metric, but squared. Okay, so the coupling function really selects a subclass of scalar Gauss-Bonnet gravity. And for the purpose of this talk, so this is not officially written down in any paper, but for the purpose of this talk, I will define a type 1 and type 2 scalar Gauss-Bonnet gravity. So type 1 is the following. The derivative of the coupling function with respect to the scalar field is always non-zero, so you cannot find a scalar field where this expression becomes 0. And examples for this are, for example, a shift symmetric coupling, or a standard dilaton type coupling that is e to the phi coupling. And in this case, the scalar field will always be sourced by the space-time curvature. So if you have black holes, they will always carry scalar hair. And I will talk about this class of, or this type of theories first. Now the second class, or type 2, has a coupling function such that its derivative with respect to the scalar field can be 0 for some constant scalar field. So this includes, for example, a phi squared type coupling or a Gaussian type coupling. And in this case, as we will see later, the Kerr solution and the Schwarzschild solution are still solutions to the theory, but they can become spontaneously scalarized above a certain curvature threshold. Okay, so what I will do now for the rest of this talk is first give you some overview of results for this type 1 scalar Gauss-Bonnet gravity. And the second half, I will focus on new results that we have found for this type 2 theory. Okay, so type 1, as I said, the derivative of this coupling function with respect to the scalar field is never 0. I will focus here on the shift symmetric coupling. All the arguments that I'm giving you will hold also for this dilatonic coupling. And what you get here is that the scalar field phi is always sourced by this type of terms. So you have this dimension for coupling constant, and then you have the space-time curvature here in the Gauss-Bonnet invariant. Yeah, so even if you start with a 0 scalar field, the space-time curvature will source the scalar field, and you will form scalar hair, as we have shown in a series of papers back in the day when I was working with Thomas Soterio and his student Robert Benko. Okay, so if we do have these hairy black holes, and you've already seen some of these arguments in Leo Stein's talks for dynamic Gershon-Simon, so the same holds true here. If we have 2 of these black holes, then and they orbit around each other, then we will source, in this case, scalar dipole radiation. And I think instead of describing that in many words, I will just show one of my older simulations where we have evolved the scalar field on top of a black hole binary. So here we are working in the decoupling limit. The scalar field is not back reacting onto the metric. We have the black hole binary in the background, and the scalar field is sourced by the background and evolves according to it. And that we have implemented in my numerical relativity library Canuda, which is publicly available and works together with the Einstein toolkit. Okay, so the example that I will show you you will see the equatorial plane, and you will see the evolution of the scalar field. The background has a black hole binary with a mass ratio of 1 to 2. So let's try that. You should be able to see the animation. So what we have here, as I said, is the equatorial plane of our binary. The bulbs here in the middle are the scalar field here around each of the black holes. As I said, we have a mass ratio of 1 to 2. And as these two black holes are in-spiraling, they're sourcing a scalar field, and you start now seeing now the scalar dipole radiation that is emitted by the system. This radiation becomes stronger in amplitude and frequency, as driven really by the orbital motion of our black hole binary in the background. You have now the merger into a single rotating black hole. All the non-axisymmetric modes are shed away, and the solution, the final object, settles down to a axisymmetric solution in scalar Gauss-Bonnet gravity. Okay, so that is in the decoupling limit, and that is really just the last about 10 orbits before merger. So let's talk about the in-spiral a little bit more. And to do that, you need to perform post-Newtonian type calculations. I'm not going to talk about any of the details. So here's just a short summary on that. One of the first works on this problem was done by Kent Yaghi, Stein, Takayuki Tanaka, and Nico Yunus here, where they computed the energy fluxes from a post-Newtonian approach in the small coupling regime. More recent work by Félix Gillier and Emanuele Berti looked at the two-body Lagrangian and sensitivities up to fourth order in this coupling. And the most recent work that we have put forward with Banafsheh Shirali-Lu and Tanya Samaya and Nestor are really the gravitational waveforms computed up to 1p order for a general coupling function and for a general coupling. So this is outside the recoupling approximation. And I know this plot looks very busy, so let me just talk you through this. And we have here, I'm here presenting you the one of the gravitational wave polarizations as a function of time, as well as the frequency evolution as a function of time for a black hole binary that has a mass ratio of 1 to 2, total mass of 15 solar masses. And for concreteness, we fixed the dimension less coupling constant here. And what we are comparing are the calculation of these polarizations in GR, which are the black curves, and in Einstein-Dilaton Gauss-Bonnet gravity, which is a blue curve here. And we start, so t equals 0 here corresponds to a frequency of about 10 Hertz. That is when the binary would enter the sensitivity band of LIGO. And what you should take away from this is that we have here really computed explicitly the gravitational waveform that shows the gravitational wave phase shift if we have a quadratic coupling to a quadratic incurvature term here. We find similar results for the shift symmetric case as well, but I'm not showing that here. Okay. So that's all I wanted to say about the first type of scalar Gauss-Bonnet gravity series. And now I will shift gears and move on to the second type. So let me just remind you, in this second class of series, and this is actually a typo, I apologize. So here we have the coupling function itself, but to be something like a phi squared or a Gaussian coupling that was studied by Daniela Daneva and collaborators, which means that you can write your scalar field equation now in the following form. So this is a general form here. If you insert the coupling function of the type phi squared, what you will get is essentially a Klein-Gordon type equation with a spatially dependent effective mass term. Moreover, what you will see is that if the derivative of this coupling function becomes 0 at a certain value for the scalar field, the solutions of GR, so the Kerr and Schwarzschild solutions, still exist. And I'm illustrating that here on the right-hand side in this phase space, where we have the coupling function in units of solar mass squared versus the mass of the black hole in solar mass squared. So all the white region here essentially corresponds to the regions where our Kerr and Schwarzschild solution still exist. And in fact, people like Caio Macedo and Hector Gata da Silva have shown that the Kerr solution is in fact unique if this effective mass term is larger than 0. So in that case, any scalar field perturbation would always decay, and the Kerr family of solutions is unique. However, if your effective mass term becomes negative, you can have a tachyonic instability, and your black holes can scalarize spontaneously. So this was a scalarized solution would correspond here to these bands shown in gray, blue, and red. That is, you can have now a coexistence of GR and hairy scalarized solutions. In this talk, I will focus on non-rotating black holes. I should mention that Alexandro Dima, who will join us here in UIC in October, has actually worked and presented results on spin-induced scalarization, because in this case, the Gauss-Band invariant itself can change sign, so you get a much richer phenomenology. As I said, for the purposes of this talk, I will focus on the Schwarzschild case, so one type of series here. Okay, so if you can have these spontaneously scalarized black holes, what happens if you put that in a binary? Now, let me take a small break and actually talk about a different theory where we also have spontaneous scalarization of a compact object. And that is neutron stars and scalar tensor series. So it has been long known that neutron stars in scalar tensor series can spontaneously scalarize, again, if their density is sufficiently large. So in this case, the scalar field is sourced by the energy momentum tensor, so by the matter of the neutron star itself. And it has been found in subsequent work that if you put these spontaneously scalarized if you put these neutron stars in a binary, you can have new effects. In particular, even if you have initially non-scalarized neutron stars, once they are sufficiently close, so once the orbits are sufficiently compact, you can have a dynamical scalarization of the final object. And I'm just using this notation here. So S bar would be non-scalarized plus non-scalarized going to something that is scalarized. You can also have the effect where one neutron star is scalarized, the other one isn't. And again, once the binary becomes sufficiently compact, you can spontaneously scalarize the final object. So our question was, when we started out on this project last fall, was, do we see something similar for black holes? And that's what I'm going to tell you for the rest of this talk. So we have implemented the new coupling functions to study spontaneously scalarized black holes in scalar Gauss-Bonnet gravity. And again, we are focusing on the decoupling limit. So we are not including the back reaction just yet. because in this case, we do control the equations and their properties, and we know that they are all well posed. Our background black holes were either head-on collisions, so really the simplest toy problem that you could think of, or an in-spiraling black hole binary. Now, the main result, and I will talk you through this in a second, is the following, that most of the configurations that we looked at actually dynamically descalarized. So unlike the neutron star case in scalar tensor series, here our final black hole typically would lose its scalar here. Okay, let me talk you through that in a bit more detail. So we are presenting here 4 different cases indicated by these Feynman type diagrams. In particular, we looked at a system where both black holes were not scalarized, mixed system where only one of the black holes is scalarized, both black holes are scalarized but lead to a non-scalarized solution, and the last case here we had cranked up the coupling so much that the scalarized plus scalarized black hole binary remained scalarized. So let me first show you an animation of the case where one of the black holes is scalarized and the other one is not. And I will probably have that on repeat because it's a rather short one. So what you see here is the scalarized black hole on the right, the non-scalarized black hole on the left. These white curves here are the isocurvature levels for the Gauss-Bonnet invariant. So what one should be able to see is that the curvature here for the scalarized black hole is somewhat larger than the other one. So the mass ratio of the black holes here was 1 to 2, and I think I just lost my mouse. So in this case, so what we see here is as the black holes collide, the curvature, Gauss-Bonnet invariant, decreases upon collision as it goes with the inverse power of the mass to the force. And after the collision, the curvature is no longer strong enough to support the scalar here. So we find this dynamical descalarization of black holes. Okay, so let me stop this now. I'm sure you have seen more than enough of it. Here we just show that same result in a bit more detail, where we have the monopole scalar field as a function of time shifted such that t = 0 coincides with the merger time. And the first 3 cases, as I said, lead to descalarization. So even if we have a scalarization before the merger, so like in this case B and C here, after the merger, the scalar here is no longer supported and just decays. Whereas this final case, we really had to crank up the coupling here sufficiently to make sure that the final black hole is scalarized. But yeah, so descalarization is really what seems to be the more general phenomenon. If you want to see more of these animations or want to look at it in a bit more detail, we have the website and YouTube channel here. Okay, so just a quick taster for the in-spiraling black hole, because that's just the first proof of principle simulation for that. We have a much larger parameter study on the way. So here we looked at the black hole binary that completed about 10 orbits before its merger. In this case, the initial black holes were both scalarized. You can see here the scalar field monopole again as a function of time, scalar field quadrupole, and for comparison, the gravitational wave quadrupole in the background. You see that the scalarized black holes before the merger do carry the scalar field. After the merger, again, they shed away the scalar field. We do find excitation of the scalar field quadrupole here, again, driven by the black hole binary in the background. So I would expect a shift in the gravitational wave signal as induced by this scalar quadrupole radiation. But then another study that's on the way is really looking at the ring down part, at the final object here, because now, unlike in this first type where the final black hole is still a hairy black hole, here the final black hole has shed away all its hair, and it's really just described by the Kerr metric. Okay, so with that, let me summarize what potential application we could have for this type. So the first one, just to recap, we do have an inspiral of hairy scalar black holes. So we have scalar dipole or quadrupole radiation that dephases the gravitational wave signal. I've also shown you now explicit calculation of the gravitational wave polarization that you can find in our paper with Banafsheh. The merger and post-merger lead to a hairy black hole that can then modify the ring down. And this type of theories are by now strongly bound from observations with the most recent papers put out by Scott Perkins and collaborators just this week. The second type that I talked about is still completely unconstrained. If your black holes are both hairy or both scalarized before the merger, you get the same story, scalar dipole radiation, dephasing of the gravitational wave signal. But you can also have situations where your black holes are not necessarily both scalarized. In particular, if you have unequal mass cases, only one of them may be scalarized. So it's still under investigation how that will impact the pre-merger evolution, and also how much we can tell about the post-merger, because in this case, the black holes may completely discharge. The final object can still be a Kerr black hole. So the question is, how does it really impact the ring down and the mergers? And with that, I come to my summary and conclusions. So I told you about a series where you have a coupling to higher curvature terms that can lead to either hairy or scalarized black holes. I haven't talked about dynamic Chern-Simons gravity, but here the story is very similar, just that you need to start with a rotating black hole to have a scalar configuration in the first place. But again, depending on your coupling function, you can have hairy or scalarized black holes. You get scalar radiation and the gravitational wave phase shift typically before the merger. But then the post-merger configuration can be different for type 1 and type 2. And as I already alluded to, so we are continuing by really performing a parameter study of inspiraling black hole binaries and looking for the spin-induced scalarization. So that's ongoing work with one of my PhD students and undergraduate students who are joining me for the summer. Another interesting question is how this would impact, or how it is impacted if we include back reactions. So I would actually be really interested to see if we can use or extend Leo's approach to the nonlinear evolution to study dynamical scalarization, including back reaction, and to predict the gravitational wave signal. And of course, then the next steps are really to identify what the observational implications are and to perform parameter studies using Bayesian parameter estimation. And with that, I thank you. I hope I didn't run over time. Hand back to Miguel. And
you're doing very well. Thank you so much, Helvi. Very nice talk. We like it. So we have time for questions. So use the hand. Okay, Aaron.
Yeah, hi Helvi. Thanks for the nice talk. I wanted to ask about the motivation for this particular type of theory, because you write down, so depending on how you truncate the function f, it's still an order 5 or order 6 operator, right? I mean, dimensional analysis.
Yes.
So what's the particular motivation for this type of operator and not a lower order operator?
So there are two types. So the fancy one is to say, oh, this you can actually derive these series in the low energy limit of string series, supergravity. And then if you reduce that down to 4 dimensions, you would get a coupling of the form e to the phi. So you would have a dilaton coupling, right? So if you take this to if you expand that for small phi, you would get this coupling to phi, if that's what you're asking about. And in some sense, this higher curvature, this quadratic and curvature term is like the lowest order term in a series of higher curvature corrections that you could think of.
But so why can't I just write down, for instance, arm mu nu? That should, I mean, just radiatively, I would expect that to be present, right?
Yeah, so you can do that, of course. But the point of looking at this Gauss-Bonne coupling or invariant in particular is that this leads field equations that are second order, so second derivatives in the metric and the field. Whereas a term of the type arm mu nu would lead to higher order time derivatives, and then we have to worry about ghosts, etc. So that was the whole point in Leo's talk. How can we get these higher derivative terms under control? Yeah, so for me, the main reason to look at this one is really the mathematical structure.
Okay, thanks. Maybe that's a point for the discussion then. Thanks.
Okay, Nico.
Hi, Helvi. Thanks for the very nice talk. I actually want to ask a clarification about one of the things you have here on the future things you can do with this Gauss-Bonne scalarization. So when you said that you would like to perform numerical evolution as Leo presented, so like with this perturbative approach, don't you think that you might miss scalarization as it is a completely perturbative effect, non-perturbative
Non-perturbative, no, you're absolutely right. Yeah, so that's why, so I'm just blurting that out there because I want to look at it first, but you're absolutely right. So this scalarization is a completely non-linear effect. So if you just look at an effective field theory expansion, you would completely miss it. Yeah, so Nicola, you are absolutely right about that. So we need to think about how we can rewrite the theory to capture these effects.
Because the problem is, like, if you evolve everything as it is, you would enter into like loss of hyperbolicity, so loss of predictivity.
That's absolutely right. Yeah. No, that's absolutely right. So that's ongoing work with Nestor Ortiz, in fact, where we think about a different approach on how to rewrite the theory more along the lines of what Lewis has done a couple of years ago.
Okay, thanks.
Which would allow us to capture these nonlinear effects. Yeah.
Okay, so thanks again, Helvi. So we are in a good time to take a coffee. So see you in, let's say, 15 minutes, 45, sorry. I don't. And okay, yeah, enjoy your coffee, tea, water, whatever. And thanks again, Helvi. Tony, are you here around?
Yes, I'm here.
¿Probamos la slides?
Sure. Okay. So let me try to share the screen.
Okay. Perfect.
Do you see it?
Yeah.
Okay, great. Thank you.
Go forward just to see if you don't have.
Go forward.
But with the slides.
Okay.
Yeah.
Okay.
Thanks. Gracias, Tony.
You're welcome.
Entonces. Eugene, are you there?
Yep, I'm here. All right, very good.
Okay. So
Yeah.
I will present you, and then you are the boss.
Okay, thank you. Well, you're still the boss, but I'll be like
No, not yet. So yeah, 40 minutes.
Okay.
We'll
Well,
move on.
yeah. Stop me if we get too far, but I think it should be fine. I think the discussion have been very nice so far. So we've been hopefully get more people.
Yeah, and thanks again for taking care
Oh
of
no, thank you. So let me share my screen. So the people.
Yeah.
I have a couple of slides to talk about, so just to get the discussion.
Perfect. And you are co-host, yeah.
Yep. All right. Can you see the slide? Can you see the slides?
Yeah, we can. So okay, we will start in 1 minute.
Good. Yeah, so apologies in advance that you might hear some screaming baby in the background.
No, don't worry. Okay, so we will start with the discussion session. So Eugene will moderate the discussion. So Eugene is a senior lecturer at King's College London. So he's very well known for his work in numerical relativity in cosmology and modified gravity. So go ahead, Eugene, you are the boss.
Thanks, Miguel, and thanks for organizing this really nice conference. I mean, I've really enjoyed it so far, and especially the discussion session. So I'm really happy to be able to moderate this session. So organizers asked me to moderate the session called Numerical Relativity Beyond GR. But I thought that it seems nice to open it up a little bit more to not just talk about numerical relativity beyond GR, but also talk about numerical relativity beyond what is normally used for, which is a lot of work been done for to calculate waveforms from black hole and neutron star mergers. In the sense, this is where numerical relativity got started, just to calculate these things. So like this is a scene from the Monty Python, where they go, what have numerical relativity what have the Romans ever done for us, right? So what have numerical relativity ever done for us beyond all these amazing things like waveforms from black hole and neutron star mergers? So what it can do for us is to go beyond these things, right? For example, like what we have heard today's great talks from Leo and Helvi to test modified gravity, and we're going to hear more talks from Paul later on. But also we can use it to test things that are not standard model, like exotic matter, like echoes that we heard several talks, including one from Paulo yesterday, and we're going to hear Tony speak later on using numerical relativity to simulate things that are not non-standard, if you like. But also beyond that, we can do things like test GR conjectures. People like Luis here has tried to look for violation of cosmic censorship, and Pau has done a lot of work on that. So it can do a lot more things than black hole and then neutron star mergers. So hopefully we can open up the discussion today. So what are the sort of like what are the key questions? So I just put this up here just to like give you a sense of we don't have to talk about all these things, but we can just give you a sense of what is the key issues here, in my opinion. Like for example, when you test modified gravity, as we have heard several talks already, what a question about well-posedness, right? Is there a bootstrap approach? And what I mean by bootstrap approach is to sort of like do perturbation theory over some like known GR solutions. So try to like bootstrap yourself up to the true solution, just like what Leo was describing. And then is there a model independent approach to doing this? And in the problem of testing exotic matter, so the question that we like to know, the answers to the question we like to know is like, can echoes be black hole mimics? What about superradiance? What about the effects of this exotic matter, this light scalar field, which is usually the case on black hole dynamics? And finally, can we use numerical relativity to test like GR conjectures? Obviously, I put I put quotation mark here and a scary GR here. Is oftentimes these are done in a higher dimensional theories, for example, in 5-dimensional black strings, etc. So, but it is still there for us to use to try to prove some of the things that we think we are just conjecturing and then haven't really quite proved it analytically. Right, so there's some common issues in using numerical relativity, and this is like the 3 that I can think about in the very late at night last night. But it sort of like boils down to the very important point when we talk about numerical relativity, that it's not a turnkey black box. It's not something that that you can say, oh, buy from Amazon and then plug it in and you solve all your problems for you. As a former cosmologist, I had a lot of cosmologist friends say, Eugene, you do numerical relativity now. Can you solve this for me? And I said, ooh. So oftentimes we get this sense that it can solve all your life problems for you, but it's not. As Leo pointed out just now, that there is actually a lot to get something to work is a lot of work. And this sort of boils down to one of the problems that we hear in this conference and elsewhere, where there are too many theories to test, right? So numerical relativity is expensive and time consuming. We have many theories to test. Which one should we look for? How do we even decide what is the right theory that you want to spend energy on? Do we try to do all of them or not? Next question, like famously, well-posedness. There's a lot of work and a lot of progress been made in the last few years. And then the last thing, which is slightly less well known, but it's still actually a problem, is that when you do numerical relativity, the first thing that you have to worry about is what about your initial conditions? It's usually hard to find. You can find initial conditions that is on constraint, but is it the right initial condition that is on constraint? That is kind of not known. Even for echoes, I don't think it's a solved problem, even just for echoes, like binary inspirals, for example. So this is kind of like the issues that I hope that we have a discussion on. And I'm sorry to be remiss by not actually introducing the panel members. So the panel members for today's discussion is the speakers for the day, which is Leo, Helvi, Pao, and Tony. And I've sort of taken the liberty to invite a 5th panel member, which is Aaron Kovacs, who have done a lot of work in the last year, solving one of the kind of major problem in figuring out the well-posedness of large class of density theory. So what I hope in this discussion is that I want everybody to speak up. If we can turn on the camera, that would be great, so that we face each other instead of facing a blank screen. And 2 is that what I'll try to do is to let the audience speak instead of the panel speak. So what I'll start here is that I will leave this screen on so that you all can discuss among yourselves. And start by talking about modified gravity theory. So we have here 2 talks from Leo and Helvi. So maybe now is a good opportunity to ask the audience whether or not they have any questions on the top that they would like to discuss with Leo and Helvi. So I see a hand put up by Aaron.
Yeah, hi Eugene. So I wanted to discuss the question of well-posedness, because it seemed to me that the paradigm is that higher derivative theories cannot be well posed. And while I do agree that they do have issues in terms of, for instance, Ostrogradsky instabilities, there do exist higher order theories. And for instance, what I would call quadratic gravity, which is just r mu nu and r squared, has been proven to be a well-posed, to have a well-posed initial value problem already in the 80s. So I think that's just something that one should be aware of, that higher derivative theories are not generally ill-posed.
Any comments from the panel? Maybe Leo, Helvi, Pao, or even Luis?
Yeah, maybe I can make a comment. So about this R-squared derivatives you mentioned. So when one deals with high derivative theories, there's one thing that one needs to take into account, which is field redefinitions. And I think for this specific theory that you mentioned, then by a field redefinition, then you can make it obviously well posed. Now, of course, one of the issues is that in general, in these higher derivative theories, you have higher than 2nd order equations, and then it's a challenging issue to sort of make sense of this equation, of this type of equations. And I think in this regard, Luis, he has a hand up here, so he has something to say. Then I think one approach that has been proven successful in another class of high derivative theories that we all know and love, namely hydrodynamics, is to apply this sort of Müller-Israel-Stewart type formulation to, on the one hand, reduce the order of the equation so that in the end you end up with a second order system which doesn't have this type of instabilities, and you can hopefully make well pose. Of course, this procedure usually has the issue that is highly non-unique. And then there's a question of since these high derivative theories, once you sort of decide to work with one specific type, then you are inevitably neglecting higher order terms, right? So one aspect of this whole problem is to guarantee that your scheme is such that those higher order terms that you decide to ignore remain small within sort of the your setup. And I think that's another issue that often arises in this context.
Thanks, Bao. Luis, you put out your hand. You want to add something to it, or you have no point?
So sure. But as a reaction to Aaron, so yes, so there are some subset of theories that are well posed, or at least locally well posed. Globally, it's a completely different story. But the majority are not. And also, one could argue any theory one picks which is a deviation from GR in, well, most theories are derived from an EFT approach. So any truncation that one considers that may be well posed should be also think of it in light of that truncation. As Pao was saying, there will be further terms that one is ignoring. And well, is it justified to ignore them? And if not, because you are pursuing some particular principle that maybe is you have a theory that is renormalizable, then those extra terms are there, and eventually there will be a term that will break rigorous well-posedness from that point of view. Of course, then there is EFT arguments and the hand waving, oh, those terms should stay small, and then there is a question with respect to what sort of initial data things are fine or not. I think in the larger context, where we should, in some sense, relax the way we think. One thing is to be saying that the theory is well posed, and that doesn't make any sense. It's the initial boundary value problem that is well posed, and it could be well posed with respect to some set of initial data, and not with respect to another set of initial data. We have already, if our anchor point is generativity and we're modifying it, well, we already know that generativity has in store regimes of initial data that lead to singularities. And so there, the gradients will blow up, will get very large, unless these extra terms somehow introduce an effect and an amazing amount of dissipation. So it might be that any theory is well posed with respect to some, practically well posed with respect to some initial data, and it's not with respect to a different one. And that is perhaps even more complicated, because now there is no way to give a blanket statement as to the theory itself, but it's a theory with respect to some particular setups.
Yeah, Luis, thanks. So can I also add a little bit more, or maybe like it's not just whether or not it's a well-posed initial value formalism, right? You said that it depends on what your value, what initial value is, but isn't that also a function of, not a function of theory, it's a function of also formalism, right? How do you write down your theory such that, or your theory of the initial condition such that it will evolve in a stable manner? Is that a fair comment to say?
Yeah, that's also very common to say. We know that we can write ADM equations, and
exactly,
well, it has some weakness, but then we can write generalized harmonics and they will not. So it also adds to that, is what particular representation one is choosing to study the problem.
Okay.
Can I don't have a hand up button because I guess co-hosts aren't allowed to put their hands up. But so I have a question going off of this point that Luis made, which is an important point, and this is really a question to the experts here on PDE theory. So I know that the typical kind of analysis is to say we know how things behave in a linear setting, and then we know that that'll control how things behave in a nonlinear setting. And I want to know the following. So we know that in GR with, let's say that we're focusing on binary black holes. So we don't have any matter, we don't have any shocks or anything. So in GR, outside of the black holes, we know that we have smooth C infinity data, and the metric decays exponentially if you like expand it in a spectral basis, for example, right? So the amount of power in high momentum scales goes down exponentially with momentum scale. And so now if I treat some other theories as deformations of GR, are nonlinearities due to the interactions that you introduce by deforming the theory, they might change the high momentum scale behavior from that background, exponentially decaying behavior. But like, what is the worst behavior that you could generate if your high momentum scale behavior in your background solution is this exponentially decaying spectral expansion?
I can just maybe, so I will latch on to the question because I think it's an interesting question, but there is a premise there that I would disagree with. We don't know that GR will have the higher momenta decay. In fact, we know the opposite. So the theorem of stability of Minkowski is in a very, very particular Sobolev space. You need to make sure that things, you don't have enough energy in higher momentum, and they are satisfying a very particular decay rate. Otherwise, you don't get back Minkowski. You actually can form a singularity.
And if I may jump onto that, which goes back to this discussion about initial conditions and which type of solutions remain well posed. So if you want to look at dynamical spacetimes, and this is what we are interested here, we have to make sure that that's still the case. So even if, say, a single black hole solution that exists can remain well posed, what happens if we have a highly nonlinear scenario as close to the merger? So this is just, really trying to point out what difficulties we may have here. And while there are proofs now in GR, even for nonlinear stability of Schwarzschild and small rotating Kerr, none of these exist really in beyond GR, right? So even the proof for stability of flat space is really not addressed if we go outside GR.
Well, I mean, I'm thinking of something much simpler. Probably, I want to be like a very optimistic physicist, not a mathematician, for the time being, and say, yeah, I know that we can have like critical collapse solutions, and we can have, naked singularities from some classes of initial data, but we also know from experience that we have spectrally convergent codes for doing binary black hole mergers. So at least in practice, in this subspace of just like close to a quasi-circular binary black hole problem, it seems that the metric is, has momentum decaying exponentially with, power decaying exponentially with momentum. So if we assumed that, like, what's the worst possible high momentum behavior that we could generate?
Well, again, let me disagree with that statement, Leo, because we also know physically other things happen, like lensing, and we have focusing. So when we throw in a dynamical this scalar field, like you guys like to talk about this in the dynamic assignments, well, we can lens that thing, and it could explore high momentum. So the fact that we haven't been doing it is because you haven't been looking for trouble. That's what I would argue, because trouble may lurk right around the corner, and also, to what extent are we justified exploring any theory without asking around a black hole, without asking first, could we actually have formed such an object in the theory? Because if we can't, then we're just talking about my usual stupid example is we're looking at a pen standing on its tip, and we're just looking around it. If that pen could have never gotten there, why are we even talking about it? And so I just, while I share your sentiment or your wishful thinking that maybe everything will work out for the best, and that's a very compelling kind of way of thinking. I'm a very negative person, I guess. I like to know that I can trust things before I can move forward.
Can I maybe defend Leo a little bit here? Is that I think I share both point of view, but I think maybe playing devil's advocate to your view is that if we have these catastrophic failures of these theories, right, and then LIGO or Lisa or Virgo haven't seen any of these crazy things happening in the sky, should we even be spending energy trying to understand them when things are sort of more or less GR as or observer has been seems to be telling us?
Awesome question. So I think we probably then need to, because I do agree that there is a part of what Leo is saying that I think that might be the relevant question. Understand a lot more about what GR has in store, and then open the envelope. Because GR, so I always also use this example. We know relativistic hydrodynamics when we include viscosity is ill-posed. That's why Israel Thor go and try and fixing it. You can go and fix it, but if you're really messing up with the physics in 3+1 dimensions, because energy wants to go to the UV and you're killing it. But you apply the same formulation in 2+1 dimension and everything is fine, because energy does not want to go significantly to the UV. And so maybe, and this one idea that we half joking around is that maybe that's what GR is doing. Maybe GR on its own really doesn't want to allow a lot of energy to go into UV. And this is a different way of saying exactly what Leo was saying. And if we understand well that, then we can do something. But we also need to understand that's true in a very restricted corner of the parameter space or the initial data space, because we know it's not true around the singularity formation. So we have to say, oh, within this context, under this corner, maybe we can do this, but we cannot say things in general.
Yeah, I think that's fair. I think that it's kind of two questions here, right? So what does nature likes to do, and what does nature is allowed to do in a way? Like we might have some very like parameter space of like measure 0 where it does go completely crazy, while most of the parameter space actually flows to this like happy regime that Leo was describing. So yeah, I'm not quite sure what the right answer is, but it seems that it's got two separate questions here.
But also, Eugene, the question is how things can go wrong.
Oh yeah,
right?
I agree.
And I think even in GR we don't know, right? So I mean, Luis mentioned critical collapse, but at least in the spherically symmetric case, we know that the singularity is at least in a codimension 1 space in the initial conditions. In high dimensions, we know now that you can form generically singularities, but those singularities seem to, for all the evidence we have, these singularities seem to involve microscopically small amount of mass. So in this case, in this high dimensional case, GR goes bad at some point, but the observational consequences of these would be completely irrelevant. So because it involves microscopic amounts of mass. So should the analogous happen in these other theories in the 4-dimensional case, then the theory could still be bad. We could not sort of simulate it beyond a certain point, but LIGO would not have seen it.
So maybe some sort of like a extended cosmic censorship principle somewhere, but all the bad things you'll never see.
Yeah, so I mean, the question is I mean, things can go bad in these theories, just as they can go bad in GR, but the question is how they can go bad, or how bad the singularities we can form are. Do they involve microscopic amount of mass or matter, or they are just really, really bad, in which case they would involve a microscopic amount of matter, which could be possibly detectable. And since we've not seen it, then you could say, well, then why bother? So, and I think that's related to this question.
Thanks, Paul. I think I agree with that. So, any other comments from both the panel members and the audience?
So, Eugene, there are some questions perhaps in the chat. I'm not sure if you.
I'm following the chat. Sorry, I should follow the chat because I am sharing the screen, so I actually cannot see the chat.
I didn't want to break the flow of the discussion.
No, please.
I mean, about the well-posed formulation of R plus R mu nu squared, but then I was prompted by Marco to this old paper in 1982 and to another paper.
I see. Okay. Thanks.
I find interesting that, as Aaron points out in his paper, there is no connection between ghosts and well-posedness.
Yeah, no, absolutely. Okay. So maybe we can move on a little bit beyond well-posedness to I was about to talk about bootstrap math and method, which is like what Leo describing, but it seems like the discussion has merged a little bit. Maybe we can like speak briefly about this and discuss briefly before we move on to exotic matter. How much time do I still have, Miguel, for this discussion?
17 minutes.
17 minutes. Okay, so maybe we should move on to types of exotic matter so that we can speak like 50-50. So the next thing we'd like to talk about is types of exotic matter. I think we have heard talks from Katie and Paolo a couple of days ago for the last 2 days, and then we're going to hear Tony's talks. So I'd like to talk like broad question for this is like, can echoes be black hole mimics? Can the signals we see in LIGO and Virgo are actually from these crazy things instead of less crazy things called black holes? Is there super radiance, and what does it tell us about ultralight scalars or ultralight bosons? Does it have any effects on black hole dynamics? So if you have like compact objects immersed in this background of exotic matter, can we possibly observe these things? So I'd like to maybe is there any questions or any things that the audience want to raise? If not, I'll ask Tony to maybe briefly describe like maybe talk about some of the main issues here.
Yeah, sure. So one of the things I wanted to say first is in connection with the previous discussion is that someone said that we first have to see what GR really has on store still, right? So before going to these very interesting, theories beyond GR that you are discussing, I think that within GR we still have plenty of room for discovery. So in particular, now that the field is finally observationally driven, I think that I'd be very surprised that all the future detections at LIGO, Virgo, Cagliari would still be the vanilla-like binary black hole detections that we are receiving so far. We still have some evidences that there are, some of the signals may be not so easily explained with your vanilla-like binary black hole model. So in particular, we have this very, very clear example with 1905-21, where there is a degeneracy, a very clear degeneracy between different models. So one very well-motivated model that can also explain perfectly well and slightly statistically better the signal is just the collision of two bosonic stars, in particular vector stars. Broca stars apparently were somewhat better than a little bit better than black holes or standard black holes. And the scalar case would be maybe more complicated to adapt to that scenario because of some possible instabilities that spinning boson stars, scalar boson stars may have. I will discuss that in my talk. So this is an open issue still, but these are still earlier steps that we're taking in that direction. But what I want to say is that within GR, the issue of degeneracy has not yet been addressed, and I think it's a very important one. We don't only have the gravitational channel, we also have the electromagnetic channel. You can also mimic the shadow of the black hole using Broca stars. For the Schwarzschild black hole, this has been already proved. So this degeneracy issue within GR is an open issue that I think merits a lot of attention still.
Okay, thanks, Tony. So any comments from the audience or any? Okay, I see hand raised. Sorry, I can't see the name. So there's
So Caio, yeah.
Caio, sorry about that. I'm not very good at Zoom, despite after 1 year doing Zoom.
No, that's okay. That's okay. So Tony, about this vector stars. So I was thinking that I saw the paper that you put out in about the collision of these two vector stars. So I imagine that if you have a spiral or something else, or even in the head-on case, you would have an additional interaction concerning the two vector fields, right? And also, I remember that when you consider collisions of boson stars, you basically have this freedom of choosing an initial phase for the oscillation. So the two stars can either have the same phase and the final results will be different from other types of collision and so on. So wouldn't this, I mean, I know that this would bring more complicated points into the matter, right? Because I mean, collisions of two black holes are much simpler than that. But could you not tuning everything to explain, I mean, a lot of types of collision with these vector stars and end up with a configuration that fits the final stage or some?
Yeah, absolutely.
You know what I mean?
Absolutely, this is a very good question. So we use the type of geometry that we choose the type of geometry that we choose for two main reasons. The first one is that we don't have constraints satisfying initial data for the binary Procastar case, for Procastar binaries. It's still an open issue, the initial data. And then also we were motivated by the type of signal. The signal from this intermediate mass black hole signal basically doesn't have a spiral part. So either it is something which is maybe it is a merger of two black holes with very high eccentricity, or with some precession, some amount of precision that can really kill the spiral part of the signal before merger, or it's something with, as I was saying, very high eccentricity, which can also be maybe considered something head-on. So the reason why we took the head-on collision was by simplicity, also because we don't have the initial data yet available for that, and also because the signal was revealing that there are no cycles in the spiral. So it's something like just a burst on the ring. And this is what we did. And for different models, we saw that it fit very well the signal. So of course, for the future, I mean, the number of detections of this type of weird non-vanilla-like signal are going to increase, presumably. So it would be very important to have initial data that satisfies the constraints, and this is something that actually we're working on here in Valencia. Unfortunately, I wasn't in the talk by Kathy last week, and I know that they have been doing also simulations of scalar fields or binaries with black holes and scalar fields and action fields. I'm not sure what is the level of the development of the initial data. I'm not sure if somebody has already managed to come up with constraint satisfying initial data. I don't think that's still the case for scalar fields and vector fields, but that would be a major thing for the near future as the number of detections increase.
Thank you, Tony.
So you also mentioned about this vector radiation. So what would be the effect? Because this vector field is not the same as the electromagnetic one, right? So it only, I mean, that's because Procastars are usually constructed from complex vectors, right?
That's right, but the signal in the end comes from the black hole itself, because the Procastars collapse before merging. So the signal that we get is a standard quadrupole. The tensor mode from the gravitational one.
Okay, so any other questions, follow-up questions on this discussions?
I actually just want to make a comment. Yeah, so, and I kind of want to point the finger at Katie, because she has done some work towards this direction, or I think it's ongoing, to construct constraint satisfying initial data in the presence of scalar fields. I myself have done that for single black holes, and I have it, so single black holes plus a massive scalar or massive vector field. So Tony, if you want to talk at some point, just ping me.
Indeed, that would be very nice. So what people typically do at the moment, as you probably know, is just to superpose the solutions and then boost them, but then this introduces some violations. So. That's right. And if you're not careful, it can actually really mess up your physics. That's right. So,
yeah.
Yeah. So thanks for pointing me out, Helvi. So I guess I should just comment. Yeah. So we are in GR Chombo. We have an initial data solver. And we're working on a version that solves general problems. I mean, Eugene also knows all about this. So, so yeah, we basically have it working, but I mean, we wouldn't sort of give it to anyone at this stage yet because it's a bit of a mess. But yeah, in principle, we can solve sort of general initial configurations for scalar or vector fields with non-trivial Hamiltonian and momentum constraints, which is what you need if you want something that's sort of spinning. Yeah.
Okay. I want to also add that solving like proper constraints, initial condition is really not enough if you want to actually understand physics, because I think you mentioned that superposition of result, even after you superpose them and then you relax them into the correct constraint surface, what you have done is that you have lost the knowledge of what your initial conditions are. Because not all, if you do not know what initial conditions are, whatever, like it's like garbage in, garbage out, right? So you do not know what you are putting in, so what you get, what is that, right? So maybe you can get some sort of a qualitative understanding of what's going on, but you don't really know. It's like if you collide two black holes, but you do not know what the mass of the black holes, what is the result that you get? So I think that is another, I think that's a separate problem of trying to understand what is the solution that you got after relaxation. And I think that's kind of open problem for in general for boson stars, I think. Kyle, you have a question or comment?
Yeah, but if you, I mean, it's just if you, it's in another direction. So if anyone have comments on
yeah, I just wanted to. I actually wanted to say that Eugene's last point was very good, even in vacuum GR, just vanilla stuff, because we have a bunch of different codes and they start with a bunch of different approaches to constructing initial data, and their parameter spaces may be different from each other exactly because of the reason that you stated. So if we want to do something really high precision, like if LIGO gets to the point where we're getting down to the 5th decimal place, then we have to figure out how to map between the parameter spaces of initial data after solving nonlinearly between the different codes, so that we can really do a fair cross comparison at like whatever decimal place we're getting out to.
So my comment was in the direction of formation of this kind of exotic compact objects, because I think Paulo mentioned it yesterday, yes, that about the formation that we usually have this zoo of compact, exotic compact objects, but the one that I think we understand the most about formations are boson stars. And even in the case of boson star, if you imagine spherically symmetric boson stars, I don't see many works considering very, very compact objects forming numerically from gravitational collapse. You see, I mean, for mini boson stars, you see for some self-interaction, there are solitonic boson stars that can be very, very compact, but I mean, the compactness reaching arbitrarily close to Schwarzschild, I think this is a point that is interesting. And I wonder if someone that deals with the full numerical stuff knows about something in this direction, and I leave this for you guys.
Katie, you raise your hand.
Yeah, but I'm kind of raising it on your behalf, Eugene.
Well,
I mean, yeah, I'll say something first, and then I'll give it to Eugene, who actually has the paper on this. But I mean, generally speaking, it is really hard to form these very overdense, very, very compact objects. So like boson stars, if you just start with kind of the perturbations that you start in any general cosmology, like cosmology simulation, and you let them evolve for the kind of cosmological timescales, they don't generically clump into these very overdense regions. Like you can't get them to sort of get to this kind of very compact regime without some kind of additional feature, like putting a bump in your power spectrum the same way as you do to generate like primordial black holes, or some kind of seeding mechanism where you seed them on some baryonic overdensity or something like this. So it's actually hard to form them. So to some extent, that's another sort of challenge to the exotic compact object paradigm, that can you get them in the first place? And I would say that you do need an additional ingredient. You need to put in some way to get them to form. But as I say, Eugene has a paper on it, so he should probably.
No, I think you've described my paper better than I could, right? So I think, so yeah, that's right. Katie have mentioned that we did have a paper on that, but all the.
Excuse me, Eugene, 5 minutes left.
Okay.
Sorry.
Right. So maybe I should, I should stop. I mean, just saying that we do have a paper on it, and as Katie said, it is quite hard to form them, but you can. But the initial conditions of forming them is fairly, you need a big spike in the perturbations. So like if you like general in inflation kind of initial condition is not going to do. You need something a lot more than that. So yeah, okay. So we have 5 more minutes. Do we have anybody? So should we try to like discuss maybe briefly on the last point, which is that
Eugene, before you go to the last point, can I actually follow up on your discussion just to clarify what your initial conditions were? So in your study, you looked at massive scalar fields only, right? So. Yes. This still doesn't address any of the questions. So, can we form any of these bosonic stars from just stellar evolution? So we really need to have some kind of exotic matter to begin with. Is that right? Would you agree with that statement?
I think I agree with that. I think up to a point, I think what we have done is, I totally agree with you in the sense that we haven't not evolved it straight from cosmological background, if you like. What we did is that we say, okay, let's just start with some scalar fields with perturbation that is sort of semi-random, and then let's just evolve it, with periodic boundary condition and see if they would want to collapse into a relativistic, highly compact boson star, and then it does that, right? But then you can ask the question, what is the amplitude of the perturbation you need to put in? And it turns out to be quite big, right? So and then you can say, can this be from some cosmological model? Kind of maybe no, because depends on how shameless you are in constructing cosmological models. If you are very shameless, then you can construct models to make them. But if you are somebody is a bit less, a little bit more I worry about your face a little bit more like me, then say, okay, well, no, it is a little bit crazy. So I think I agree with you up to a point.
Okay, thanks.
Okay, thanks for the questions. So we have like a couple more minutes left. So maybe instead of going to GR conjectures, maybe you can ask the question that is sort of like self-flagellating a little bit. Is that, and then hopefully I don't offend anybody here. Is that so we have the problem that Luis mentioned in the modified gravity part bit, where we say that, well, okay, why do we consider anything beyond GR, right? So here in our case. In the exotic matter. So why are we working? There's a lot of work done, and I'm no party to it. I did a lot of work on this. But why scalar fields? Why boson fields? Why is it justify your existence, right? Why do we? And we usually have the story that, okay, well, maybe ultralight scalar field could be dark matter. Maybe string theory give us some lot of these axion-like particles. We haven't discovered WIMPs yet. So, but are these good justifications? If we are honest with ourselves? Maybe I could put it out to the audience and not just the panel. Do you feel that this is strong enough justification to spend a lot of CPU hours and a lot of brain power to solve this problem? It's a bit provocative, right? But I think it's a fair question. At least I ask myself before I go to sleep in a bad night.
So usually from my point of view is that scalars are the simplest form of the matter that you can have, right? So if you consider scalar plus GR is just the simplest configuration that you can get from a gravity solution, right? I mean, I'm not going through, because if you usually deal with baryonic matter, you will need microphysics, you will need an equation of state, and for scalars, you don't even need that. Right, so you just have a scalar field, and let's see how it goes. So it's just from my perspective that usually make me sleep at night. It's just the simplest thing that you can do, and there are some interesting stuff that goes that you can find using this kind of configuration that illuminates a lot of discussions that you have beyond that. At least that's what I think.
No, I think I agree with you. It is kind of a placeholder for unknown physics in many ways, and it is, in a sense, a degree of freedom that we understand. Katie, you raise your hand, please.
Okay, I'll attempt to defend us, all of us. Like the way I see it, like we're kind of in training, right? Aren't we sort of in training for when we do see something unexpected in like LIGO or LISA? You know, we're not going to immediately know what it is, but we're going to have some ideas about, you know, these are the things that it could be and these are the things that it couldn't be. So I think individual things, yeah, you can certainly question like how motivated it is, but I always feel like we're just kind of warming up for, you know, the data that we're going to get, and you know, eventually we're going to see something that we don't expect, and we want to be kind of ready for it at that point and have some ideas about which ways it can go. So that would be my defense. I don't know if anyone agrees, but that's what I would say. That's how I get to sleep at night.
Okay, so any comments? Anybody who wants to like challenge this point or support this point or suggest how you go to sleep at night? If not, I think we might be just on time. Is it the right time to finish? I think
Perfect time.
And it's a nice ending. So thanks, Katie, for defending us, right?
Yeah, thanks, Katie.
I'll hand it back to you, Miguel.
Yeah, perfectly, Eugene. We are perfectly on time. So thanks again. Oh, I lost my, okay. To all of you for a very nice discussion. So let's move with Pau. So Pau, if you want to share your screen, I will present you.
Yes. See.
And
yeah, is it visible?
Oh yeah. Sorry. And I have a problem with my Zoom now. Just 1 second. What happened here? Okay, I lost my track with the presentation, but okay. Pau Figueras is from School of Mathematical Science, Queen Mary, University of London. So today he will present us binary black hole mergers in qubit-Hornbensky theory. So go ahead, Pau. Thanks.
Well, thank you very much. I would like to first start by thanking the organizers, all of them, for organizing such a wonderful meeting in the present difficult circumstances, and for inviting me to speak today. As I'm sure many of the other speakers, I would have loved to be able to give this talk in person. But I think one of the advantages of the current format is that there are probably many more participants that could have taken part in the workshop. As Miguel said, I'm going to talk about work that I've been doing in the past year and a half or so with my PhD student, Tiago França, whose name appears here in red. And the reason why his name is highlighted is because he's done all the hard work that I'm going to talk about today, so he deserves all the credit. And I strongly suggest that you write down his name and you keep him under the radar, because he's an absolutely brilliant PhD student, and you want to take him into account when he applies for postdocs, because he will not disappoint you. All right, so after having said all of this, let me get started. I'll first start with some motivation, but today is the last day of this conference, so if you make it to this point, then you must be truly motivated, regardless of what I'm going to say. But let me reiterate some of the main points that all of them have been already mentioned before in this conference. So I think we are now in the era of gravitational wave astronomy. This offers us the opportunity to learn about the fundamentals of gravity, either if it's described by general relativity or by some other more fundamental theory. And we can do that by studying and analyzing gravitational waves produced in the merger of compact objects. And precisely through these gravitational waves, we can test the strong field regime of gravity in a new way. And as Alessandra mentioned in her talk, by now there are more than 40 plus confirmed public events corresponding to binary black hole mergers plus 2 neutron star mergers. But the situation is only going to get better because the current detectors are going to be upgraded, and a new generation of detectors may become operational in a years, and finally LISA. So in the near future, we will be carrying out precision tests of gravity through gravitational waves. So all the data we have, my understanding is that the deviations from GR are small, and this is going to be important in the rest of this talk. So in terms of having a better understanding of gravity through studying gravitational waves from compact objects, is that we do need to obtain the predictions for such events in alternative theories of gravity, precisely in the strong regime. And this is challenging. This is challenging for the following reasons. So firstly, as we've seen extensively in this workshop, there are many alternative theories of gravity. Each one of them modifies GR in some unique way, and presumably the uniqueness of each of these theories should be imprinted in the gravitational waves that should be produced if one were to simulate, say, a black hole in such theory. So since there are so many theories out there, then it's not clear what should we be looking for. So if there was a preferred theory, perhaps we could design new methods to try to extract the strong field dynamics of such theory, but we don't have that yet. So any approach should be somewhat general at the moment. Another issue is that many such alternative theories of gravity are not known to be well-posed. So the issue of well-posedness has been mentioned before, but in some cases, this is just a question of gauge. We have not been able to find a suitable gauge. But if you want to simulate, say, a binary black hole, one needs to find a well-posed version of the theory in order to extract the predictions for the gravitational waveforms, which one would then compare with GR and perhaps either find what modifications of GR are out there. So there are possible ways forward, which again have already been mentioned. One is to, given a theory that for some reason we like, just try to find a well-posed version. And this has been successfully applied in a number of cases, in particular in the Hortensky class. And then these results have been used to simulate black hole binaries in these theories. And this is the approach that we're going to take today. Another approach that has been mentioned and carried out to great success, I would say, by Leo and collaborators is linearizing around GR. After all, this seems to be justified given that the modifications of GR are small. And another proposal that was put forward by Luis and collaborators is to modify the theory using inspiration from relativistic hydrodynamics and try to construct a well-posed version using, as I said, these analogous formalism to the Mueller-Israel-Stewart formalism that renders relativistic viscous hydrodynamics a well-posed theory. So these, in some respects, this has Luis and collaborators have successfully done this in some examples, but I will not discuss this any further today. So, oops, okay. So furthermore, in today's talk, we will concentrate on black holes. The reason is that in any theory of gravity, black holes are the simplest objects, and they have a full description within the theory itself. And after all, by studying the dynamics of these objects, we can access the strong field regime of the theory, which is what we are ultimately interested in. There are other gravitational objects of interest, such as neutron stars, boson stars, etc. But these other objects typically involve other non-gravitational physics, which is often poorly understood or difficult to model in practice. So for these reasons, we will just focus our attention on black holes. So let me just quickly outline the rest of this talk. So first, I will review for you cubic Hortensky theory. Since I said today is the last day of the talk and Hortensky theories have been mentioned extensively, so I assume that by now you would all be experts on such theories, but nevertheless, I will just explain again. Then I will discuss the weak field regime of this theory. And this is important because of some of the issues that were mentioned in these in the discussions that we just had, because that relates to the well-posedness of the theory and the validity of this theory as an effective field theory. And then I will just present some preliminary results that we have on black hole binaries in these cubic Hortensky theories and compare them to GR. And I will finally conclude. So if there's any question during the talk, just feel free to interrupt me. All right, so let me just quickly remind you of the cubic Hordensky theories. So Hordensky theory, the general one, is the most general scalar tensor theory of gravity with second-order equations of motion that arises from diffeomorphism invariant action. And it's typically written in terms of these Lagrangian consisting of 5 terms. So the first term is the usual Einstein-Hilbert term with a canonical kinetic term for the scalar field and an arbitrary potential. And then the other terms, L2, L3, L4, L5, are just deviations, higher derivative corrections to these Einstein-Hilbert term. And the details of these terms are not important. All I just want to stress is that this is a highly nonlinear theory, which, as you can see, involves higher derivatives. And the motivation in this talk, just subscribing Katie's motivation, is that we'll use it as a toy model to try to understand what kind of issues may arise when one simulates higher derivative theories. In this case, the higher derivatives are just in the matter sector, and matter is the simplest possible form of matter, namely scalar field. But we will see that some of the issues that are encountered in these theories could also be happening in a more general higher derivative theory, which involves higher derivatives of the metric. After all, we know that even though there are many possible corrections to the Einstein-Hilbert action, definitely higher derivatives corrections are out there. So the question is how large they are and whether we can detect them with gravitational wave observations, and that is not known. So the cubic Hordensky theory consists on taking the first 3 terms in the previous action. And the reason why we use this particular theory and not another one is because of a reason of convenience. So Aaron Kovac, which is also here in this conference, so he proved that cubic Hordensky theory is well posed, again, assuming that the initial data is, let's say, also well posed, in the standard BSSN or CZ4 formulation of the Einstein equations and in puncture gauge. I also want to mention that the general Hordensky theory, which involves all the 5 terms in the Lagrangian, in the previous slide, was also recently shown to be well posed in a modified version of the generalized harmonic gauge, again, proposed by Aaron and Harvey Rihal. But I will not discuss this general case any further today. So just to write down more explicitly the cubic theory, as we just seen. So these, you have, first of all, the Einstein-Hilbert term here, and then there are 2 other terms which encode the higher derivative corrections of the cubic Hordensky theory. Now, these functions, capital G2 and capital G3, are in principle arbitrary functions of the scalar field itself and x. X is just the standard kinetic term for the scalar field. So when one wants to simulate this theory, you have to make a choice. You have to pick up some values of these functions, capital G2 and G3. So the values that these functions that we picked are the following. So for G2, we just chose to be just some coupling constant, dimensionful coupling constant, small g, and x squared. And this term can be motivated from the point of view of EFT, because as Weinberg showed, this is the most general scalar term up to 4 derivatives that one can add to the action. And for G3, we just picked the simplest possible term, which just, again, a dimensionful coupling constant and x. And when we do the simulations, we will be always thinking in the weakly coupled regime, which means that the corrections to the Einstein-Hilbert term should be small. So you can think of that you may Taylor expand these functions G3, and then this G3, the term that we pick, would be one of the first few terms in such an expansion. But that's just motivation. And again, our main motivation to study this theory in the nonlinear regime is to just get some understanding of what kind of effects one could expect should one simulate black hole binaries in a higher derivative tensor theory of gravity. So none of the conclusions that we obtained should depend on the details of these functions big g's that we pick. So we hope to get some more general understanding of what may happen when one incorporates high derivative effects in gravity. All right, so let me first discuss what we mean by the weak field regime of this theory. So in our work, we take an EFT approach. So we think of this Hordensky theory as coming from truncated higher derivative theory, so which has infinite terms, and we just decide to pick the first 3 terms in the cubic Hordensky theory. So in order for this to make sense, it must be possible to argue that the higher order terms that we ignored should be okay to neglect them. So the terms that we pick that correct Einstein-Hilbert term should remain small. Otherwise, it would not be justified to truncate the theory to the just 3 terms that we pick. Even though we want these corrections to the Einstein-Hilbert term to be small, this is compatible with these nonlinearities becoming important. And again, the whole point is that we want to be able to argue that the higher derivative corrections that we do not take into account are not important. I should also stress that the well-Poisson's result that Aaron proved only holds when precisely these terms that correct Einstein-Hilbert action are small. So for the class of theories that we picked up, this notion of smallness compared to the Einstein-Hilbert term is captured by these conditions that you have here at the bottom. So here, the G2 or G3, these are the coupling constants, which are free parameters in our action. And we want to compare these dimensionful couplings to the typical length scale that you get from Einstein-Hilbert, which in this case, is just say could be either the curvature scale arising from the metric or derivatives of the scalar field. So we say that we are in the weakly coupled regime when again these inequalities are satisfied, and this ensures that the corrections to the Einstein-Hilbert term are small. So even though these corrections introduced by the Hordensky theory to Einstein-Hilbert are small, we will treat them fully nonlinearly. So I just want to stress that even these corrections are small, one could treat them perturbatively, as Leo has advocated, but one has to be careful with secular effects. And again, Leo has provided possible solutions, but as is well known, and Leo explained very well in his talk, secular effects can render perturbation theory invalid in a regime when it should still be applicable. So one has to be very careful in how you treat these secular terms. But more importantly, by doing this perturbative expansion, one may miss certain non-perturbative physics. And one example of this is, for instance, the nonlinear stability or instability of ADS, when one has been studied extensively in the high energy physics community, and one can perform this nonlinear perturbation theory, one can do resummations, and yet any perturbative approach will miss, for example, non-perturbative effects such as the formation of a black hole. So in our approach, where we treat the theory fully nonlinearly, then we have access to such non-perturbative physics. And we hope that this is something that can allow us to distinguish these theories from GR. So our first goal is to identify the weakly coupled regime of these theories in the space of initial conditions and couplings. And as Luis stressed in the discussion, this is part of what it means for the theory to be well posed. So we want to identify the region also in the space of initial conditions such that we can construct global solutions for arbitrary times to this Hordensky theory, and moreover ensuring that the correction to the Einstein-Hilbert action remains small throughout the evolution. Also, since so to do that, what we will do first is to study gravitational collapse in these theories. And this is also a convenient way to obtain black hole binary surrounded by a scalar cloud, because when you study collapse, then indeed part of the scalar field will go into forming the black hole, but there will be some leftover scalar field lurking around the black hole. And we are interested in the dynamics of any interactions of the scalar field with the black holes and see how they differ in Hordensky and GR. So to study gravitational collapse, we just pick the simplest possible spherically symmetric case of just a Gaussian profile, which depends on an amplitude and some radius and a width. So these are 3 parameters that we can tune, and we choose this scalar profile to be ingoing. And one can see that in the space of initial conditions, the strength of the Hordensky terms, namely the corrections that the Hordensky terms introduce to the Einstein-Hilbert terms, are just measured by these dimensionless constants, eta 2 and eta 1. So what we want to make sure, we will say that the theory or the initial data is weakly coupled when these 2 dimensionless constants are suitably small. And what we do is we solve the constraints. So we start with constraint preserving initial data, and then we will evolve it and see what happens. So one important thing to bear in mind when one solves these theories is that the evolution of the scalar field in this case is not controlled by the space-time metric, which is what would happen in standard GR, but by an effective metric, which depends on the scalar field and its derivatives. So the fact that in higher derivative theories, some of the degrees of freedom the evolution of such degrees of freedom depends on an effective metric is a generic fact of such higher derivative theories. And one consequence of this is that the hyperbolicity of the scalar equations of motion depends on the hyperbolicity of this effective metric. And this metric may cease to be suitably hyperbolic when, as you can see, when the derivatives of the scalar field become large. So it is possible that you start with initial data, which is perfectly smooth and suitably small. So you would think that you are in the regime of the effective field theory, but you may exit this regime as evolution proceeds. And another aspect is that because these effective metrics depend on the scalar field and its derivatives, then in principle, shocks can form from smooth initial data. So the phenomenology of how hyperbolicity breaks down in such theories has been studied extensively in the literature, and I will not describe it here, but just to say that it's, in this case, even though one starts with, say, acceptable initial data, it's not all clear that singularities may develop in the future. And precisely understanding when this happens and for which regions in the initial data happens, this is precisely our first goal. So just to give you an example of some simulations that we did, and that's for G2 class theories. And here what we do is we monitor the determinant of the effective metric and this time-time component of the inverse of the effective metric. So these are 2 quantities that are useful to study the hyperbolicity of the system. The details, again, are not important. So in this example, so what we did, we fixed the coupling constant to some value, and then we varied the amplitude of the scalar field. And so the amplitude increases as you go to the right. So you can see when the amplitude is very small, so the deviations of these 2 quantities from GR, the GR values, which are 1, are pretty small. So this is indeed, so you would conclude that in case 1 and 2, you would be in the weakly coupled regime. But in this case, the amplitude of the scalar field is too small to form a black hole. As you increase the amplitude, then you end up forming a black hole, as you can see in cases 3 and 4. In this case, because the scalar field follows an effective metric, then there is a scalar horizon, which is a sound horizon for the scalar field, which if the Hordensky terms are suitably small, this will be close to the black hole horizon, which is here drawn as a solid line. So the scalar horizon is this dotted line. Another quantity that we measured is this weak field condition. So we want to make sure that this weak field condition remains small during the evolution. And here in these dashed curves, just show the region where this weak field condition is order 1. So we want to make sure that this weak field condition is suitably small outside, on and outside black holes. Inside black holes, I personally think that it's okay if the weak field condition is violated. After all, we know that GR breaks down near singularities, and so will any of these effective theories. So as long as this region where this weak field condition inside the apparent horizon of the black hole is sufficiently far from the apparent horizon, in principle, the breakdown of this theory should not influence observers outside. On the other hand, if you increase the coupling constant in this theory too much, then everything goes bad. So here is, in case 1, is an example in which the coupling constant is large, but the amplitude of the scalar field is small. So you would start with initial data, which is, you would think it's perfectly okay, but to the future, the hyperbolicity breaks down. And you can see here that the weak field condition is order 1, and there's no horizon that can hide this. So this, we would deem this as not as initial data which is not allowed, or which would take us outside the regime of validity of effective field theory, and therefore we would discard these initial conditions. And the others are just another example. So in the case number 4, you can see that even at the level of the initial data, the weak field condition is violated. So in this case, we would discard these initial conditions straight away. But that's just shown for illustrative purposes. In all of these runs, eventually the hyperbolicity of the scalar system breaks down, so we cannot continue the evolution beyond a certain point. And as I said, the details of how this happens are not important today. So after all these studies, after running loads of simulations, we obtained this diagram where the blue region would be represents the region in the space of initial conditions where this theory would be well posed and in the regime of validity of effective field theory throughout the evolution. So in this blue region, we can construct global solutions to the Hordensky theories such that they are always in the weakly coupled regime. So in these yellowish regions, so these are regions where the initial data is weakly coupled. Let's say the corrections are small, but you exit the regime of validity of effective field theory at late times. So if hyperbolicity eventually breaks down, so you want to stay away also from these yellow regions. The green regions are just regions where the weak field condition is violated, even at the level of the initial data. So that's not allowed. So this black band here denotes the region where near critical collapse. So to the left of this black band, you do not form black holes. So the scalar field disperses, and to the right, you form black holes. So if we want to simulate a black hole binary, we want to choose initial data, which is in the blue region to the right of this black band. So we did not study the details of how and when these Hordensky theories are applicable near critical collapse, because that's more subtle. So that's why we just decide to stay safely away from this region. But that's also an interesting problem on its own. So just to summarize, again, the blue region to the right is the region which we identified in this particular class of Hordensky theories as a suitable region where the theory is well posed, and we can construct global solutions which are weakly coupled throughout, and therefore in the regime of validity of effective field theory. So what we will do next is to consider black hole binaries with initial data in this region. So that's just a summary of what I've just said. So now let me move on and discuss the black hole binaries. So again, we consider these Gaussian scalar profiles that collapse. We consider massive scalars. We also consider massless scalars, but with massive scalars, they are sort of more useful in some respect because the scalar field stays around the black hole for longer, so we can probe, so we can hopefully have a larger effect. So I should say that even though for the collapsing case, we solved the constraints, so when we consider binaries, we just superpose two of these lumps that are constraint preserving. So when we superpose them, they are not constraint preserving. But we put them far apart so that the amount of constraint violation that we have initially due to superposing these two lumps is very small, and we can safely identify it in the signal. And we will see a waveform shortly. when this is quite obvious. So I insist that we make sure that the initial data is well posed. We're in the weakly coupled regime, and we arrange these two lumps such that they collapse in a very short time. And the black holes, which have some scalar field surrounding them, they describe 5 orbits before merger, and these orbits are eccentric. So consider eccentric orbits, even though they may not be observationally as frequent as the nearly circular orbits. If one wants to study a strong field regime, they turn out to be quite advantageous because one has better access to the strong field regime of the theory for longer in such orbits. So that's why we considered eccentric orbits, also because they are somewhat easier to find. And so here, even though we know that the initial data is in the well-posed regime, we want to make sure that throughout the evolution of the binary, the weak field condition remains small. So we will monitor this weak field condition. And just to say that because inside the apparent horizon, even GR breaks down, these theories also break down, we excise a portion which is far away, sufficiently far away from the apparent horizon. And that just makes the evolutions more stable. Okay, so without further ado, let me just show you one example of a binary. So this is a video produced by Tiago. So in this case, you see the initial scalar cloud, the 2 black holes form. They describe 2 close bys in the eccentric orbit, and finally they merge. So let me just show it again, just because it's very nice. So the scalar field initially collapses, forms 2 black holes. They get close to each other. You can see, so these blue regions, I should say, so that's the energy density of the scalar field. And you can see that remains non-trivial throughout the evolution, even on and after merger. So if we take a closer look at one snapshot of the binary before the merger, again, this blue region is the energy density of the scalar field, which is quite small, of the order of 10 to minus 5, and it's larger near the black hole horizon. So that is that's what we are interested in, because in this region, scalars in this theory coupled curvature, so you would expect that you may have enhanced effects due to the higher derivative terms, precisely in the regions where the space-time curvature is large. So here, these orange circles are the horizons of the individual black holes, and this reddish region inside is the region where the weak field condition is order 1. So as you can see, throughout the binary, the binaries that we have simulated, we have ensured that this weak field condition is small on and outside black hole. So we have reasons to trust that our simulation is well within the regime of validity of effective field theory. So let me just show an example of one of the waveforms that we've obtained, and that's for one of the G3 theories, but the main features, they are the same in all the theories that we've considered, even G2. So the red curve is the GR curve. So here's just a GR coupled to a massive scalar. And then the blue curve is the Hordensky theory. So the initial wiggles that you see before time 200, these are the initial constraint violations that we have due to superposing 2 scalar lumps. And the wiggles that you see at around 250 or something, and around 600, these are the gravitational wave bursts that you see from the close encounters of the eccentric binary. So these are not constraint violations, these are like real physics. And here, what is should have said, what's shown here is the real part of the psi4 scalar of the L equals to M equals 2 mode. So the perhaps more salient feature that one can see in these waveforms is that there's a very clear dephasing between GR and Hordensky. Even though the Hordensky terms are very small throughout the evolution, the binary of in Hordensky happens later. Oops, sorry. And that's all something, this effect, this order 1 effect, is something one can already see in the second close encounter of the binary, even before.
It is my computer or Pau left?
No, I think it's Pau.
The evolution
Okay.
over
Pau,
Yeah.
sorry, we missed you for like 3 minutes.
Sorry, my connection is a bit shaky. So what I was saying is that, so this is an example of a situation in which the corrections to GR are small throughout the evolution, and yet we see an order 1 difference between GR and Hortensky. And that's something which is already visible at the second near encounter of the binary. And by the time we reach merger, then clearly the waveforms look significantly different. So we are still analyzing, we still have to analyze in more details of these waveforms to identify more features. But yes, it seems that this is an example in which one can see large differences, even though the terms that we have in the action are small throughout the evolution. So that's quite interesting, in my opinion. So
Pablo,
yeah.
Pablo, quick question. On the non-GR case, are you measuring these waveforms in the Jordan frame? And because there is a significant difference, but I mean, after merger, they're very similar. So I'm just trying to understand that.
So what do you mean Jordan frame? So GR, we just have a standard scalar.
No, in the non-GR case. In the non-GR case.
No, in non-GR case, we're measuring everything in Einstein frame.
And is that the correct thing?
Well, whatever we care about is what the test mirrors in LIGO are doing, right? So what are the test mirrors coupled to?
I mean, the physical frame would be the Jordan frame, right?
Right, that's what I think. That's
the Jordan frame. Why the physical frame you say is a Jordan frame?
Because that's where meta couples non-minimally to the metric. And that's where it's essentially the frame where you perform measurements and observations.
That's right. So I will need to think about the details of these specific theories that we picked, whether this is an issue or not. But I doubt that this will change this dephasing.
Yeah, actually, I have a question about that, but I will hold off until the discussion session. Just a few moments.
I'm actually just going to jump to the conclusions, if you allow me to continue. So basically, the conclusions are just what I just said, essentially. So we've done this Hortensky. So something that I didn't mention is that, of course, so one issue is that, so we've got this thing working for a while already, but we haven't published it yet because it's subtle, and we need to make sure that we understand the errors. So after all, the corrections to GR are very small. And we need to make sure that this dephasing is not something that is due to errors accumulating, which may be large in these high derivative theories, but it's something that is real. So we think that this is something that now we fully understand and is under control. So for all theories that we've considered, then we see the same this feature, that there's an order 1 dephasing when we compare GR to non-GR. It doesn't depend on the sign of the couplings. It doesn't depend on the sort of details of the function. So if it's the same for G2 or G3 theories. So we believe that this is something that's, that seems to be quite generic for this class of high derivative theories. And perhaps one may attribute this to that these theories have a strong UV cascade. So there's more energy transferred to the scalar field. And that's why then the binary is delayed. But we still have to fully analyze and understand the details of this. So so with this, I suppose I'm already nearly out of time, so I'll just stop here.
You are doing very well, Pau. So thank you so much, Pau. Very nice talk. So time for questions. First, I think is Helvi who raised the hand. Right.
Yeah, sorry, I cannot raise my hand as one of the co-hosts, but so a very nice talk, Pau. Thank you. Can you go back to your last plot about the waveform? Because one of the features that I find quite intriguing is that it seems that that the phase shift leads to a delay in the merger. Is that because of having an eccentric binary or not? Because in most cases that we have looked at, where you have this additional scalar radiation that actually accelerates the in-spiral, right? So we have the non-GR signal before the GR signal.
Right. Again, so the GR case, again, is an eccentric binary. So for both cases, we are simulating eccentric binaries with the same total ADM mass. So that's one of the constraints that we do. Yeah, I really don't know what to answer. So this, I doubt that this is due to this being an eccentric. I mean, it would be interesting if that was the case, but I don't think that that's related to this being an eccentric binary. I don't see why this would have anything to do with the eccentricity. I think this has to do with the dynamics of the theory and the fact that and the interaction with and the nonlinear terms that you have,
No, but it's,
and which are important near the black hole.
Exactly, I completely agree with that. It's just curious that you seem to find this opposite behavior from what we would expect in other theories where you have scalar fields present.
Okay, so next question, Luis.
Yeah, so maybe this is a follow-up as well. So yeah, the strange thing is you have in the case for Horndeski, you have an RF field, in principle an RF field that can take energy and angular momentum away from the system, and yet the merger happens later. That's why I was asking where there might be a significant offset in time by doing the calculation in the Jordan frame. But you're right. I mean, the difference is so large that it would be very surprising.
Yeah,
but then physically would be very strange. So somehow this would be saying that this Horndeski field is not allowing angular momentum to be radiated away as efficiently as in GR, which, given that the terms stay small, this would be strange, right? So that's, I mean, it's very interesting, though very confusing.
Yeah, I mean, unfortunately I cannot say, I cannot give you the reason why this happens. This is what we seem to observe for all the cases that we've tried. Like I said, it doesn't seem to depend on the sign of the Horndeski coupling, or the sign of the theory itself. It's the same for G2 and G3. So perhaps, again, the scalar field lurks around. It's more efficient at sort of, as you say, just sticking around the black hole in this Horndeski theory and preventing angular momentum from being radiated. But yeah, we haven't done a sort of detailed analysis of how these various angular momentum or energy are radiated and compare them to GR. And I think that's something which we need to do to understand this better.
Thank you. Thanks.
Okay. Josu?
Yeah, I mean, I think this is even more simple, but something that we have seen sometimes in other cases is, how do you know that this dephasing cannot be related to the moving puncture gauge? Just because the puncture evolves, like the lapse evolves different for the Horndeski or the GR simulations, and that can cause also this delay. Because here, when you are plotting the x-axis time, this is just simulation time, right? It doesn't take into account the lapse anywhere. Would it be a reason for the dephasing?
I doubt that it's this. I mean, this is time, if you want, where you do the extraction, so that's far away, right?
Yeah, but that's true. But the gravitational waves can travel also through regions where the lapse is close to zero. For example, if you are close to the, for example, when the two black holes get together, right? The gravitational waves that are produced there are going through regions of lapse that are around 0.1 or 0.2.
Yes, that's indeed the case. But again, I think the point is that the correction, at any given time, the difference that you would see from, say, doing this in GR and doing this in Horndeski is small. So I don't think that at the instant of time that you see that the gravitational wave traveling to a certain region, the deviation that you would see from Horndeski and GR would be order 1. It would be small. So I doubt that this is what you say.
Good, thanks.
Yeah.
Okay, so yeah, there are one question for Leo. Can you extrapolate to infinity, including the scalar needed to change to the Jordan frame? I don't know if you want to discuss this one, Leo, or we can use the Slack channel. You can use the 6th day, and we can put all of the questions and go through the Slack channel. because we are a little bit over time.
Yeah, okay, let's continue on Slack. I don't need to take up time here.
Okay, thank you so much. So thanks again, Pau. Very nice talk. We enjoy. So let's
I'll stop sharing then.
Yeah, thank you. So Tony, can you share your screen? So, okay.
Can you see the screen?
Yeah, we can see. Thank you. So now we have Jose Antonio Font. Jose is a full professor at the Department of Astronomy and Astrophysics of the University of Valencia. He's an expert of large-scale supercomputing application in relativity astrophysics scenarios, in particular in the field of numerical relativity, hydrodynamics, and numerical relativity with exotic compact objects. Today, he will speak about the stability of spinning bosonic stars. So,
okay, thank you, Miguel. It's for me a great pleasure to be here at this conference, which is very nice. I thank the organizers for setting this up, given these appalling circumstances that we're living through. So, yeah, I'm going to talk about stability of spinning bosonic stars. This is work done with a number of collaborators here. You can see in the screen. So the real work has been done by Nico Sanchez-Wall, who is now a postdoc in Aveiro University, and Fabrizio Di Giovanni, who is a PhD student in Valencia. So for the simulations, I'm going to be showing here the results of the simulations. If you can see animations of those simulations, you can go through to this website that you can see on the screen. By the way, do you see my mouse?
Yeah, we see.
Oh, thank you very much. So yeah, so this work was in part motivated by some recent results from numerical simulations of binary mergers of boson stars that Carlos Valenzuela, Miguel Bezares, and collaborators did recently. And those simulations show that the end result of the okay, so how do I go back? All right. Can I go back? Okay. Let me do a video as well. Yeah. So those simulations found that the final product of the merger was a non-rotating boson star. So we thought about that, and we decided to investigate the issue of the stability of spinning bosonic stars, both in the scalar case and in the vector case. So why boson stars? So already Kati gave a very, very convincing argument of why it is interesting to study boson stars. But in addition to that argument, I would say that one of the most compelling reasons, in my opinion, is because of the imitation game, what you could call the imitation game. There are recent observations that of dark matter objects that support very, very well, very strongly the black hole hypothesis, like the LIGO-Virgo observations of gravitational waves, the very long baseline interferometry imaging of M87 by the EHC collaboration, or the orbital motions near the center of our galaxy. However, in spite of these observations, I believe that the degeneracy between the black hole model and additional models remains a central question. In particular, also very recently, as I mentioned in the discussion before, there are recent illustrations that have shown that dynamically robust bosonic stars can imitate the data that we are observing. And this has been actually done in two channels, both in the gravitational channel and in the electromagnetic channel. So the first example is the interpretation of 1905-21 as a merger of vector bosonic stars, Proca stars. And the second example is that this same kind of objects, Proca stars, can very easily mimic the shadow of a non-rotating black hole. So it's, in my opinion, it's worth to keep investigating this kind of exotic compact objects, this particular kind. So the focus of this presentation will be on two topics, and to analyze the stability properties of spinning bosonic stars. And I will show that under quite generic circumstances, I would say, but I will show some counter examples towards the end of the talk. Scalar boson stars, if they are spinning, they are unstable to non-axisymmetric deformations, and vector boson stars, in some cases, can also be unstable to non-axisymmetric deformations. And this bears a lot of similarities with a case that is much more studied in the literature, which is the case of rotating neutron stars, which are known to be subject to this non-axisymmetric bar mode deformation if the rate of rotation if the degree of rotation is sufficiently high. Now, if these stars are unstable, they are to bar mode deformations, they are going to have large quadrupole moments, and they are going to emit gravitational waves. And I'm going to show you that indeed these waves are quite interesting because they could be within reach, depending on the mass of the bosonic particle, of course, but they could be within reach of current detectors and maybe future detectors, which opens the possibility of probing, the existence of these hypothetical objects so far, right? So, right. So the framework is, we would use a massive complex scalar or Proca field minimally coupled to Einstein's gravity. So I'm in good old Einstein's gravity in GR, not beyond GR at all. And so we solve the Einstein Klein-Gordon system and the Einstein Proca system. You have the action here in the slide, and the Lagrangian for the scalar case and for the vector case is given by these standard quantities here. Now, for some range of parameters, these boson stars, in particular in the spherical case, have been considered since many years now, like viable black hole mimickers, because the lowest energy star, what we call the fundamental family, they have a formation mechanism that was already shown back in the 90s by Seidel and Suen, and it has also been shown recently by Di Giovanni et al. in the vector case, and they are perturbatively stable. So the way these systems are built is using these ansatz for the space-time metric with these 4 metric potential, which depend only on the radial and the theta coordinates, F0, F1, F2, and omega. And then this is the ansatz for the scalar field, which has a harmonic time dependence. And so one has to solve a system of 5 coupled partial differential equations for these fields and 2 constraint equations. So in the vector field case, there is an additional constraint due to the Gauss constraint, in addition to the Hamiltonian momentum constraint from GR. So in general relativity, scalar spinning boson stars are a mass torus. So they form a discrete set of families of continuous solutions, and we can label these families by the winding number, the azimuthal winding number m, and by the node number n. So the fundamental family are the models that do not have nodes across the star, and the winding number is n equals to 1. Now, if we fix the family, these stars are characterized only by their mass and their angular momentum j. So this is the answer that we will choose, that the potential is the scalar potential, the scalar field amplitude has this harmonic dependence e to the power of I m5 minus omega t. So here I'm showing 3 different models for scalar spinning bosonic stars. So we have the m equals 1, m equals 2, and m equals 3 cases, all of them for the fundamental family with no nodes across the star. So if you look at the energy density distribution of this, the mass energy density distribution of these objects, you can see that for in the scalar case they have this toroidal topology in GR. So this particular model I'm showing here on the left corresponds to this particular frequency value and mass value, ADM mass of the model here in this field circle that you can see on the right panel. So the ADM mass of scalar boson stars has a maximum value, which is given by the Planck mass squared divided by the mass of the particle and some coupling constant alpha. So in units of giga-electron volts, so this is a very, very small quantity, this maximum value of the ADM mass. So in order to reach values of astrophysical interest, masses of the order of a few solar masses, then you have to use values of the mass of the particle, which are extremely small, right? So these are the so-called ultralight bosonic fields. So in the vector case, the first models were reported as excited states, so n=1 models, which means that they had a node across the star. And the fundamental family was, in fact, studied later, somewhat later. The metric ansatz for the scalar case is exactly the same, but the Proca field ansatz is a little bit more complicated. So this would be the ansatz for the potential, one form of the scalar field, and the field strength is computed from the differential of this quantity. Now the energy distribution for the vector spinning stars in the fundamental family is that their density, their energy distribution, instead of being toroidal, now is spheroidal. So I'm plotting here the surfaces of constant energy density for a vector m=1 spinning boson star with these values of the frequency, mass, and angular momentum, which corresponds to this star here in the plot on the right. Okay. So as I was saying before, the dynamical formation of spinning boson stars is something that we have investigated. This is also related to the question that was raised in the discussion about the formation mechanism for this object. So we have studied the collapse of a Gaussian cloud of bosonic matter, which collapses due to its own gravity, and we have investigated if the final object is a stable object. So this was already known from spherical symmetric studies, as I was saying before, by Seidel and Suen in the 90s. And for the case of Proca star, this has been done more recently in the spherical symmetric case. And also for mixed stars formed by a fermionic component, so a neutron star plus a bosonic component. It has also been possible to show that in the spherical symmetric case, these stars can also form dynamically. So in the spinning case, our work was in full 3D, includes flotation, and was done for both scalar and vector bosonic stars. So this has been shown in these two papers here. So the type of initial data we use for the scalar case, for the m=1 scalar case, is this expression here. This is our Gaussian cloud, which has a width sigma and a given amplitude a. So the radial dependence has this particular dependence, r times this Gaussian term. And then sine theta is just the corresponding 1,1, L=1, M=1 spherical harmonic that gives the angular dependence. We have also perturbed these initial data in some of the cases, and the evolutions have been done with the Einstein toolkit. So the message to take home is that all the evolutions for this in this scalar case show the emergence of an axisymmetric instability. And the time scale at which this instability appears depends on the initial perturbation and on the amplitude of the perturbation. So what our simulations have shown is that the initial shape of the energy distribution, which was toroidal, transforms into an spherical distribution, so a non-rotating model. So all the angular momentum is shed away, is transported away, and the final product is a scalar boson star which is non-rotating. So it seems that the scalar spinning bosonic stars can be transient states in the dynamical formation scenario. So this is an example of one of the evolutions. Animations of these simulations can be found in the website that I mentioned at the beginning of my talk. So these are different time snapshots from the top left part to the bottom right part. Time increases. So you can see that at t=0 is the initial state. You see this toroidal shape. The bar mode instability develops around time 4000. This is the second snapshot. Then there's a fragmentation of the star in two clouds. These two fragments merge like a kind of binary merger. Here they recollapse and form a deformed spinning star. It breaks again, and then this process goes on until the final state is an spheroidal star. So by the end of the simulation, if you look at the values of the frequency, the mass, and the total angular momentum of the system, the values are given by these quantities here. And if you compare with the asymptotic values of a static scalar star non-rotating in the fundamental family, you can see that the values are these ones, which are very close to the values that asymptotically are reached during the dynamical formation scenario. Now, if you plot, if you add self-interaction terms in the picture, essentially, depending on the amplitude of the self-interaction, so the amplitude of the self-interaction in these different plots increases from top to bottom, and from to the left to the right, you see just the time evolution of the different models. So the larger the self-interaction term, the longer it takes for the instability to appear. But these self-interaction terms do not quench the instability. It ends up appearing anyway. So if you look at the angular momentum distribution, this is the blue curve here. You see that when the bar mode instability saturates, when the bar mode instability is triggered, there is an abrupt loss of the angular momentum, and then asymptotically it approaches the value of a static fundamental family non-rotating boson star. All right, so in the vector case, the situation is a little bit more complicated regarding the initial data, because in addition to the Hamiltonian and momentum constraint, one needs to solve also the Gauss constraint. But this was possible to be done in these two references I was mentioning before, and we evolved both unperturbed and perturbed models. So we saw that the unperturbed models are completely instability-free for very long simulations of the order of 10 to the 4. That would be of the order of hundreds of light crossing times. So these are really long time evolutions. So in the end, we get that the final system oscillates around the equilibrium value, but not too much angular momentum is shed away in these systems. So in the case of n equals 1 scalar boson stars, we see that they are subject to this non-asymmetric instability, and the same family, the n equals 1 spinning Broca star, which have a spheroidal shape, they are not affected by the instability. So this is the evolution of one of these n equals 1 vector stars, and you can see that in the end, you have lost the frequency of the final system is the same of the initial system. There's some loss of mass, but the loss of angular momentum is really very, very small. So in the end, the system is just oscillating around a central static configuration, which is still rotating. So in addition to this dynamical formation of these objects, we also constructed static solutions, the equilibrium families of solutions, because this also allows to study more compact models in particular, and to analyze much more this dichotomy found in the dynamical formation scenario. So the models that we have investigated are written in this table here. So that we have 2 scalar models and 5 vector models. 2 of them are in the fundamental family, so there are no nodes across the star, and 3 of them are in excited state. These are the models 3, 4, and 5. So they have 1 node across the star. So in the scalar case, this is an example of the scalar case. These models are much more compact. These are equilibrium models, which are much more compact. You can perturb them. And in this particular case, you also see the appearance of the bar mode instability. But since the model initially was much more compact, this particular model collapses to a black hole, as you can see here on the right by the appearance of a apparent horizon at some point during the evolution, and the lapse function goes to 0 rapidly. So clearly, even in the fundamental family, equilibrium models of spinning bosonic stars in the scalar case, if they are sufficiently perturbed, they are prone to this non-axisymmetric instability. Now, in the vector case, they show no sign of instability. The models in the fundamental family, the n equals 1 models, so with no nodes across the star. But if we have excited models, we have that highly perturbed excited solutions with 1 node across the star, they do collapse to a black hole. Okay, they are unstable, but they do not develop this bar mode instability. Now, what we did as well was to build models for spinning Broca stars with the azimuthal winding number n equals 2, and these have a toroidal shape, which is, the same kind of shape that the n equals 1 spinning scalar stars have. So we conjectured that the end state of the evolution of these stars was the appearance of the bar mode instability was related to the fact that the initial topology of the stars was toroidal in the unstable models instead of spheroidal in the stable ones. So for the n=2 spinning Procas stars also have this toroidal topology, and indeed they are bar mode unstable as well as scalar m=1 spinning boson stars. So yeah, so it seems it's related to this topology. So what is the nature of this instability? What is the reason that produces this growth of non-axisymmetric modes? So since this is something that happens in the realm of neutron stars, of highly rotating neutron stars, we decided to investigate if the same situation is at work here. So in the case of rotating stars, the neutron stars, the condition is that the differential rotation has to be sufficiently high in order to develop the so-called dynamical bar mode instability. So if the rate of rotation is not so high, the instability can appear secularly instead of dynamically. Now the amplitude of these modes, I mean, you can study the growth of the amplitude of the first non-axisymmetric modes by doing the Fourier transform of the evolution of the different modes by a Fourier analysis, and then you can compare these evolutions to the case of neutron stars, which is much better studied. So what I'm plotting here in the plot on the top is just the time evolution of the volume integrated azimuthal density Fourier mode decomposition. So we have the density and we compute the Fourier decomposition of these modes. And then I'm plotting here the first 4 modes, m=1 to m=4. And you can see the typical growth, exponential growth associated with the appearance of the instability in this system. So in the very long, so at later times, the m=2 mode is the dominant one. So if you compare this time of evolutions in our unstable spinning bosonic stars, the type of results that people have obtained in the neutron star case, you can see that the type of results are identical. They look very, very much alike. They look very much the same, right? So in the end, you have the dominant mode is also the quadruple mode towards the end. So in the neutron star case, it is well known why this evolution is like that. So this instability appears if the spinning neutron star has the so-called corrotation radius. So this is a kind of resonance effect that happens when the frequency of the modes is equal, of the unstable mode is equal to the angular velocity of the star at that particular point. So this is the so-called corrotation radius, the radius where the angular frequency of the unstable mode, which is the so-called pattern frequency, is equal to the local angular velocity of the fluid. The pattern frequency is given by this expression here, and this is our ansatz for the evolution of the instability. Sigma m is just the growth rate of the mode, and omega m is the mode frequency that you can obtain by Fourier transforming the time evolution of these coefficients. Now in practice, we just take the case n=2 because it's the dominant one at later times. And the angular velocity of the bosonic star we define in this way here. So we have the phi component of the angular momentum divided by the energy density. So we have to look into regions of the bosonic star, the spinning bosonic star, where this condition is fulfilled, that the pattern frequency is equal to the angular velocity. So this is what I'm plotting here in this plot. The plot on the top is the n=1 scalar spinning bosonic star, which is unstable, and the plot on the bottom is the n=1 vector spinning bosonic star, which is stable. The dashed black line in both plots marks this horizontal black dashed line is the location of the pattern frequency. And then the profiles is just the radial profiles of the angular velocity across the star, okay? So the solid part of these curves is the part of the star which is within the 95%, the 95% of the energy of the star so this marks the radius of the 95% of the energy of the star, and the dashed part of the curve is outside of that 95% radius, right? So you can see that at the initial times that you can see in the red and the yellow and the red and the orange curves, you see that there is a corrotation radius inside the star in the scalar case. But at later times, when the spheroidal object has already been formed towards the end, there is no corrotation point across the star. So the angular velocity is always below the pattern frequency of the mode, okay? So that's why the system is stable at later times. in the vector case, you see that initially, I mean, so what the vector case is stable. So what it has is oscillations around these equilibrium values. So you have here some of the plots corresponds to the moment of maximum expansion, and some other of the lines corresponds to the moment of maximum contraction. And then you can see that either the corrotation point is outside of this 95% radius, or the angular profile is so shallow that you can actually really produce this instability. Okay. So on a dynamical time scale, these vector spinning bosonic stars are really stable. Okay, so now models which are unstable are going to produce gravitational waves. So what I'm plotting here is the mode decomposition of the Newman-Penrose scalar psi4 for 3 different modes, m equals 0, m equals 1, and m equals 2. Initially, this is for the unstable scalar case, right? Initially, you have the green curve is the dominant one, which is the m equals 0 mode. So this is a purely axisymmetric mode. Initially, this is the one that dominates. But from this point onwards, from 10,000 or something like that, which is where the dynamical instability is really active, this non-axisymmetric instability is really active, the mode that dominates is the m equals 2 quadruple mode. Okay, this is the dominant in the gravitational wave emission. Now, the funny thing is that contrary to neutron stars, here there is no dissipation mechanism that can kill these gravitational waves. So the thing is that if these systems radiate, if these systems exist and they are prone to these instabilities, they are going to radiate. And if they radiate, there's not going to be a physical mechanism that can suppress this emission. So this is going to be a continuous emission of gravitational waves. Now, if you compute, depending on the value of the mass of the ultralight boson, since the mass of the system scales with the mass of the boson, you can fine-tune your simulation in order to make your I mean, these are the power spectrum density of the evolutions of the psi4 quantity. You can actually compute the spectra for different masses, and you can see if they agree with the sensitivity curves of the ground-based detectors, the LISA detectors, and even PTAs. So and you can see that the gravitational wave frequency of these systems can actually lie in the frequency band of these different gravitational wave observatories. So I'm not saying that this is correct, that this is real. So this is just a model so far, but in principle it may offer a potential means to establish the existence of these hypothetical stars if this kind of signals were detected. Now, this is the horizon distance for these objects. What you can see in the top is the mass of the particle in electron volts, from 10 to the minus 11 electron volts to 10 to the minus 19 electron volts. And in the bottom, you have the mass of the final systems from 1 solar mass to 10 to the 10 solar masses. So the curves on the left is the horizon distance for ground-based detectors, like the current light of Virgo and Cagram. The green curve in the middle is the corresponding horizon distance for LISA, and the one on the right is the corresponding horizon distance for PTAs, right? You can see that you can reach redshifts of the order of a few tens, which is quite interesting. Now, this mechanism, how much time do I have, Miguel, by the way?
13 minutes.
13?
Yeah.
Oh, okay, so I was going really fast, unnecessarily fast. Okay, so these simulations that I was showing you clearly show that this instability, this bar mode instability, is at work for your standard Lagrangian for scalar and vector boson stars, including self-interactions. Now, what would happen if more fancy, terms were included in the Lagrangian? And this is something that people have recently done. Simonsen and East recently published a paper where they consider different phenomenological modifications of the Lagrangian in terms of nonlinear interactions in the potential, considering axionic potentials, solitonic potentials, and different kinds of potentials. And they found that in some cases, so for n equals 1 mini boson stars, so the mini boson stars are the so-called boson stars that only have the mass term included. They found, Simonsen and East found that these mini boson stars are unstable So in agreement with our results, they also found these corrotation points and so on. But however, they found regions of the n=1 boson star parameter space where the addition of these nonlinear interactions to the scalar potential in principle can quench this non-axisymmetric instability. So this is quite an interesting result, which obviously shows that this is not the final word. So more investigations are needed in order to see if this type of instabilities are actually operating or not. Now, perhaps a simpler and maybe, well, an interesting mechanism that can also quench this instability is through a cooperative stabilization mechanism that we have put forward very, very recently. This was submitted last March to the archive. So what we are doing is that instead of considering just one scalar field or one vector field, so I'm showing here results just for one scalar field, for scalar fields, but this is also the case for vector fields. Instead of considering just one scalar field with a given frequency, we have a combination of 2L+1 multiple scalar fields, in principle also with the possibility of having different frequencies. So this is something that people like Bonazzola and Ruffini already in their original papers in the 60s already mentioned that I mean, you can have combinations of scalar fields with different frequencies and even at different states. So the ansatz for the metric potential for the metric is exactly the same that we were using in all the results that I have been showing you, but now we have each scalar field has this dependence with different frequencies Nj, total of 2L+1 different frequencies. So in the case of in a spherical symmetry, so if you do the spherical ansatz would mean to transform this metric into a metric with omega = 0. This metric potential here, omega, would be 0. F1 and F2 would be equal, and then there would be no theta dependence. And if we further assume equal frequency and equal radial amplitudes, these 2L+1 scalar field boson star families are the so-called L boson stars that Miguel Alcubierre and collaborators recently also put forward. So these L boson stars essentially are superpositions of all possible n multiples. Okay. So if you don't take into account, if you don't do this spherical ansatz, if you still take the general ansatz for the metric that you have at the top, and you solve the equations for every frequency and every field, okay, then new multi-field, multi-frequency boson star solutions emerge. Now, we have found recently that you can find that these unstable solutions that I've been discussing here can be stabilized by a hybrid L construction. Now, if we add to one of these models which is unstable, we add a sufficiently large L = 0 fundamental boson star, then, and with a different frequency, then the system is stabilized. So the model that was unstable is no longer stabilized. So one of these spinning toroidal stars, if you add an spheroidal star with different frequencies, completely stabilized. Okay, so this is another mechanism that could in principle be at work. Similar results have been, or similar cooperative stabilization mechanisms have been found in the context of excited purely boson stars. So purely boson stars are known to be unstable. However, if you superpose an excited solution with a fundamental solution, so depending on the number of bosons in the excited star and in the excited state and the fundamental state, depending on that ratio, then you get a stabilization or not. So this is something that Argelia Bernal and collaborators found some years ago. And also in the case of fermion boson stars, we have recently found that excited boson stars with a fermionic part can also be stabilized. So it seems that the cooperative mechanism not depends so much on the type of matter that you add in order to stabilize an otherwise unstable solution, but it's a purely gravitational effect. And this could also have relevance in connection with the rotation curves of galaxies. So adding scalar fields in the galactic halos in order to stabilize the rotation curves on the galaxies themselves. So these are interesting avenues that one can investigate taking into account these stabilization mechanisms through cooperations of different boson stars, more than one boson stars, or even different types of matter. Okay, so my conclusions of the conclusions of these talks is that the nonlinear dynamics of spinning bosonic stars is quite interesting. N=1 scalar spinning bosonic stars are affected by non-asymmetric instability. They migrate to these non-spinning boson stars that were also found in fully non-linear numerical relativity simulations of merging boson stars. The final object was non-rotating. A standards of interaction potential simply delays the appearance of the instability, but doesn't quench it completely. But the results of Simons and Amis adding nonlinear interactions can actually kill the instability. Now, N=1 vector spinning bosonic stars are stable because of the topology is spheroidal, and N=2 they are again unstable because they are again toroidal. They have a toroidal topology. Now, the responsible of this instability ultimately is the presence of a rotation radius inside of the star. And this is in complete analogy, absolutely similar to the case of spinning neutron stars. It's very, very, very close, the analogy. Now, I have also discussed the detectability prospects in terms of gravitational waves from these objects. And this is quite interesting. I mean, observations might be within reach of future experiments, and this offers a potential means to establish the existence of these objects. So I'm very, unlike Luis, who is a very pessimistic person, I am a very optimistic person. And I am sure that the new observational campaigns of LIGO, Virgo, and Cagra will unveil new interesting signals, waveforms that cannot be really, approximated using the standard approximations for binary black hole mergers. So, of course, the open issue of fine-tune initial data for mergers is interesting in order to see if the final object resulting from mergers is a stable spinning bosonic star, and this is an open issue as well. So thank you very much for your attention. If you want more details on this work, you can go to these two references where everything is explained in much more detail.
Okay, thank you so much, Tony. Very nice talk. I really like it. So let's go for the question. I think Eugene, go ahead.
Hi, Tony. Thanks for the nice talk. So I have a question. I mean, I had as a caveat, I had a baby interlude halfway through when my baby walked in, so I might have missed like a few minutes of the talk. But so maybe you have spoken about it there. But do you have any comments about the recent work by Dimitriev, Panin, and Levkov and Kachev about like the angular momentum loss mechanism in boson stars? I think they did it for non-relativistic system, but they did comment that in your relativistic system it should have the same kind of a mechanism. Do you have any thoughts on that?
Yeah, it did. This is my fault. I should have included that reference. We saw it a couple of weeks ago. It was in the archive a couple of weeks ago. It's the Newtonian limit of our superposition mechanism. The same kind of superposition works in the Newtonian limit. So I think they do it for the, they do it for the Schrödinger equation, I think, or.
Yeah, exactly. They do it for the Schrödinger equation. I think they do a non-relativistic limit, basically.
That's right. So it's a very interesting work and completely agrees with our result in the relativistic case. I should have mentioned it. I apologize.
No, I mean, I'm not trying to like say that you should cite them. I'm just wondering whether or not, because they did mention your work, which is to say that they think that the mechanism, so they say that, the mode loses energy, the angular momentum like mode get decayed.
We do cite the work in our revised version of the paper. We do cite the work as well.
Okay. Thanks a lot.
Okay, more questions?
Actually, I have one, if I may.
Yeah, Helvi, I lost your question in the chat because.
In the chat, yeah. Tony, very nice talk. Thanks. You talked about these multi-scalar field models just a couple of slides ago. So my immediate question was, how do you couple the scalar fields to each other? Do you have an explicit coupling, or is it really just gravitationally?
Gravitationally. They're minimally coupled. Yes.
Okay. Good. Thank you.
Of course, you can think of different couplings, but so far we have done it gravitationally.
Okay. Thank you.
And we have Hannes.
Yeah, so my question is more about the beginning of the talk, where you showed that the angular momentum decays. And so are you saying if you would you continue the simulation, the angular momentum would decay completely to 0?
We believe so. By the way, nice seeing you again, Hannes.
Yeah.
We believe so. Yeah, these were already quite long simulations. This is 3D, so it was already quite time consuming. But yeah, I'm trying to find the slide. This one, right?
Yeah, exactly.
Yeah, so the final value for this one, I don't think I wrote it. So this one is 0.16, the value at the end. So it's not really 0 yet. But yeah, so we just thought that, yeah, it would go to 0 asymptotically, but we didn't continue, to be honest.
Okay. And can you also tell me how do you actually compute the angular momentum? There's a formula, okay.
Yeah, you have the expression over there. Yeah. So it's essentially the T phi component of the stress energy tensor of the field.
Okay.
Okay, more questions? I want to ask you something. This is just a comment and a question. So what is the hope? Maybe Eugene as well or Kathy want to say something. What is the hope to have a Lorentz initial data for boson star, in your opinion, Tony?
You mean a constraint satisfying initial?
A Lorentz, like Lorentz for neutron star, but for Lorentz for... Can you comment or the...
For binaries?
Yeah.
Okay, so I don't know about Lorentz, but we are working locally here in Valencia. Fabrizio Di Giovanni, he is working on extending, you know, we have an elliptic solver in 3D to solve isolated objects. So Proca stars, spinning Proca stars, spinning boson stars, spinning neutron stars. So what we are doing at the moment is just to superpose these two stars, as everyone does. And then after the superposition, we compute the metric. So we solve the Hamiltonian momentum constraints for that metric, but then we have to recompute the matter terms, right? But you can always build the stress energy tensor for the fields that result from the solution, from the new metric, right? From the new metric. And then if you recompute the stress energy tensor for the new metric, you can then go back to the Hamiltonian momentum constraint and iterate until convergence. So this is something that we are working on at the moment, but this is an independent effort to Lorentz. So yeah.
Yeah, because I don't know, if we are thinking in the future and we want to have a ton of simulation of boson star and we can see something, we need some templates and maybe.
On the other hand, the level, I mean, if the field strength is not very high, the level of violation of the constraint is really very, very low. And it doesn't go with time. So if you can separate the two objects sufficiently in order to have the jump radiation, you know, to disappear, I think that we are still safe. But of course, it would be great to have constraint satisfying initial data. So in fact, one of the things that we want to do, so we want to do a catalog of Proca star mergers and boson star mergers if they turn out to be stable in the end. So why do we want to do that? Because we want to build actually approximants like people do for binary black holes. You can do the same for Proca stars and boson stars. Because I really think that in the future, we may have surprises. And we should be ready to have these approximants also in the. I mean, what I'm talking about is to develop an effective one-body theory for Proca star binaries, or a post-Newtonian approximation for Proca star binaries, to study also the love numbers of these objects. So all of that, all of that information is badly needed, I think, for now that we're entering the gravitational wave astronomy.
Okay. Thank you so much, Tony. So any comment? Someone want to add something? Okay, so thanks again, Tony, for a very nice talk. And okay, it was a pleasure to have all of you here, guys. I will miss you. And see you. I hope to see you next year in person. Stay safe. Enrico, if you want to say something.
Yeah, I just wanted also to thank all the speakers of today and those of the previous days, and the moderators who did an excellent job, and the chairs. And well, I don't know if she's still around, also Jomila, who actually made the organization completely smooth and seamless. So it would have been much nicer to have you in person here. So hopefully next year or very soon. Stay all safe, and thanks for staying till the very end.
Thank you.
Thank you.
Thank you. Yeah. Thanks to the organizers. But maybe we should give a clap to the organizers.
Bye-bye. Thanks, guys. It was really nice. Very well done.
Bye-bye.
Okay.
Bye-bye.
Bye.
Thank you.
Bye. Thank you.